Siberia is one of the coldest and most remote regions on Earth, a land that hides more than it reveals. Beneath its ice, forests and endless plains lie stories that reach across time, strange craters, vanished cultures, frozen creatures, and events still unexplained by science. Each mystery is a reminder that even in an age of satellites and supercomputers, there are still places on this planet that hold their secrets close. Por-Bazhyn, the lake island fortress with no clear purpose, Tuva, far out in the mountains of southern Siberia, where the wind scrapes the surface of frozen lakes and summer feels like a brief memory, an island rises from the still waters of Lake Terrakol. On that small island stand the remains of something strange. High clay walls, fragments of timber, and the faint outline of a vanished complex. Locals have known it for centuries, calling it Por-Bazhyn, the clay house. From above, it looks like a fortress, rectangular and symmetrical, resting quietly in the middle of nowhere. But no one truly knows why it was built, who lived there, or why it was left behind so suddenly. The story begins with the first explorers who reached this isolated lake. In the late 19th century, Russian researcher Dmitry Clements visited the site and recorded what he saw: collapsed walls and traces of courtyards, eroded by weather and time. Decades later, in the 1950s and 60s, Soviet archaeologists led by Semyon Weinstein carried out the first proper excavations. They found solid clay ramparts, fragments of burned wood, and evidence of careful construction. Yet they also noticed what was missing. No thick cultural layers, no dense remains of daily life, no graves, no major refuse. It looked as if the place had been built, used briefly, and abandoned. In the early 2000s, a new expedition arrived. Backed by the Russian Academy of Sciences and several universities, scientists used modern tools to probe the ruins. They brought ground-penetrating radar, drones, and even acoustic mapping to read what lay beneath the surface. Using radiocarbon and tree ring dating, they traced the origin of the wood used in construction. One discovery changed everything. Inside the timber was a signal left by a known cosmic event, a burst of radiation that struck Earth in the years 774 to 775. This allowed researchers to date the site precisely to around the year 777, placing it in the era of the Uyghur Khaganate, during the reign of Bogu Khagan. That date ruled out earlier theories and gave the site a clearer historical context. The Uyghur Empire had strong cultural ties with Tang Dynasty China, and the architecture reflected that influence. The walls were built with the Chinese hangtu technique, layers of tamped clay reinforced with timber. The complex measured about 200 meters by 160, surrounded by ramparts up to 11 meters high. There were gates aligned to the cardinal directions, courtyards laid out in perfect symmetry, and a central building raised on a platform. Fragments of roof tiles and painted plaster hinted at bright colours and elaborate decoration. Wooden brackets carved in the same interlocking style used in Chinese palaces suggested a shared architectural language across thousands of kilometers. But beauty and design are only part of the mystery. There are signs of destruction. Some walls show cracks and sudden displacement, as if shaken violently. Charred remains tell of fire. Geological surveys suggest that one or even two earthquakes struck this region around that period. One might have hit during construction, another after the site was already occupied. Combined with fire, they could explain the sudden collapse of buildings and the incomplete state of many structures. Still, earthquakes alone don't explain everything. There's barely any sign of life at Por-Bazhyn. No large storage pits, no domestic artifacts, no food waste, no trace of agriculture. It seems no one lived here for long. So the questions continue. Was it a fortress, a palace, a monastery, or something else entirely? Many archaeologists first assumed it was a fortress. The massive outer walls, corner towers, and controlled access points suggested defence. Yet the inner spaces were too refined for military use. There were no barracks, no armories, no stable foundations for heavy occupation. And the island itself, isolated in a high mountain lake, made logistics difficult. Supplying soldiers here would have been nearly impossible in winter. Another theory proposed that it was a summer palace, a royal residence built by the Uyghur elite, who ruled across Mongolia and southern Siberia. The precision and artistry of the construction fit this idea. Perhaps it was meant as a ceremonial retreat, a sign of power and connection to Chinese culture. But again, the timeline doesn't fit neatly. Within just a few years of construction, the Uyghur ruler Bogu converted to the religion of Manichaeism, and political instability spread through the empire. When Bogu was killed in a coup around the year 780, his faith fell out of favour. If Por-Bazhyn had been turned into a Manichaean monastery, that event could have sealed its fate. This leads to another theory, that Por-Bazhyn was indeed a religious centre. The architecture has a calm, orderly layout. The central building, with two main halls connected by corridors, resembles the plan of a temple or monastery. But there's a problem. Excavations haven't found any clear signs of religious life. No inscriptions, icons, manuscripts or altars. The floors are almost bare. If monks ever lived here, they left behind little trace of their presence. Others think it may never have been finished at all. The builders may have chosen the island without understanding how unstable its frozen ground really was. As soon as the foundation shifted, cracks appeared, and the project was abandoned before completion. The fire damage and partial collapses could have happened later, long after people had left. There are even more imaginative ideas. That the site was a ritual or astronomical complex, aligned with the stars or the sun. Its symmetry and orientation could point to ceremonial meaning rather than practical function. But Siberia's climate offers few clear nights, and there are no ancient records describing astronomical use. So these interpretations remain speculation. Each explanation carries fragments of truth, but none is complete. The fortress theory explains the walls, yet not the isolation. The palace idea matches the decoration but not the short occupation. The monastery concept fits the period's religion but not the lack of artifacts. The geological data show natural disasters but don't reveal human purpose. What remains is a mosaic of signals surrounded by noise, a structure rich in form but poor in narrative. Today, Por-Bazhyn continues to attract scientists from many fields: archaeologists, geologists, climate researchers, even seismologists. The 2007 and 2008 excavations collected more than 40,000 fragments of clay, wood and tile. Using laser scanning and 3D modelling, they've rebuilt digital versions of the fortress to simulate how it looked before destruction. Drone imagery shows the clear geometric precision, a layout that seems deliberate, almost ritualistic. Beneath the lakebed, sonar mapping revealed that the island itself has been slowly shrinking. Climate change and permafrost melt are eroding the very foundation on which the fortress stands. As the structure collapses, scientists race to record it. They've found traces of pigment that once coloured the walls, bits of red, black and ochre plaster. They've sampled the timber beams for DNA of ancient trees and microscopic fungi to understand the building's environment. Even the clay carries clues, minerals that tie it to local sources, showing that the builders used material from the lake's edge. Every discovery sharpens the picture, but the meaning remains elusive. Why build such a monumental complex in a land of earthquakes and frost, so far from trade routes and population centres? Why invest so much effort in beauty, symmetry and imported craftsmanship for a site that may have been occupied only for a season or two? Why did its builders vanish without a trace, leaving behind nothing but silent walls and frozen clay? Por-Bazhyn stands as a riddle in the Siberian landscape. A fortress without defenders, a palace without residents, a monastery without prayers. It defies simple explanation. What endures is the quiet rhythm of stone and wind, the echo of an empire's ambition now reduced to patterns in the earth. The more we learn, the more the silence speaks, and the less it tells us. Patomskiy, Kolpakov crater. Deep in the Siberian taiga, far from roads and towns, lies a mound that could easily be dismissed as a natural hill, except that it isn't. The Patomskiy crater, or Kolpakov cone, rises more than 40 metres above the forest floor, a steep ringed cone of broken limestone blocks, crowned by a smaller central dome. To approach it is to step into a mystery written in stone, where every crack, every layer, every shifted block is a clue in a puzzle no one has yet solved. Vadim Kolpakov first brought scientific attention to the site in 1949. The locals already knew of the structure. They called it the Fire Eagle's Nest, but Kolpakov recorded its shape, a giant cone about 160 metres in diameter at its base, tapering upward, with a circular crown and a smaller mound in the centre. Its sheer oddity stirred debate at once. Was this the remnant of a violent cataclysm, or was it a slow geological process masquerading as one? When geologists arrived decades later, they set up camps around the cone, cutting trenches, collecting rock chips, measuring strata, and mapping angles. Every stone was weighed, every fracture photographed. They mapped the debris cone's zoning, outer ramparts, inner slopes, central dome, like pages of a crime scene file. The materials are mostly broken limestone from the Marinsk Formation, with occasional sandstone and shale inclusions. The lack of exotic meteoritical metals in the samples cast doubt on early impact proposals. Radiocarbon dating offers only indirect help here, because the rocks predate the crater, but scientists turned to the forest itself. Analysis of tree rings around the mound suggests the formation is comparatively young, roughly 300 to 500 years old. Some trees that grew near the cone show an abrupt narrowing in rings around 1841-1842, and some even fell in those years. But in the decades after, ring widths widen again, then widen and narrow in puzzling cycles. Such anomalies hint at environmental stress, perhaps a burst of heat, shock, or chemical change disturbing growth. The mound's shape also suggests an explosive origin rather than a slow build-up. The concentric zones, uplifted edges, and central dome resemble the pattern left by steam or gas bursts inside rock. One favoured model today is a phreatic explosion. Superheated water trapped in subsurface rock becomes steam, pressure builds, fractures pop outward, and a crater is blasted. In the case of Patomskiy, geochemical analyses show that the oxygen isotope values in the limestone debris differ measurably from unaltered limestone nearby. That shift implies the rock interacted with hot fluids, water heated above 100 degrees Celsius, before it blew out. In effect, groundwater heated by faulting or magma may have ripped through brittle rock in a sudden roar. Still, that hypothesis has challenges. No volcanic vent or magma chamber has ever been identified nearby. The region is not known for active volcanism. What's more, the crater lacks lava, volcanic ash, or telltale magma dikes. That absence makes geologists cautious. If the steam explosion came via magma, where is the magma now? If not magma, then how did such heat reach the rock? Some proposals suggest decompression of heated groundwater zones in faulted rock. Essentially, the earth cracked, pressure dropped, and hot fluids flashed into vapour and blasted outward. The debris cone might then be arranged by multiple small explosions over time. Its layering, fracturing, and ringed ramps may reflect pulses, like ripples in water. Others once championed a meteorite impact. A high-speed projectile slams in, vaporizes, blows out rock, leaves a cone. But for that to hold, we expect impact signatures, shocked quartz, high-pressure mineral polymorphs, traces of iridium, or metal fragments. In Patomskiy's rock record, none of those have been reliably found. Chemical zoning does not show the cosmochemical anomalies that mark many known impact craters, so the meteorite theory has lost favour, but it still persists in popular imagination. Some wild ideas have danced at the fringe: nuclear tests, secret uranium works, or extraterrestrial devices. In fact, local tree ring data has been compared to radiation spikes, since after Chernobyl tree rings showed similar burst growth, but measured radioactivity in the crater is low, and none of the known records support any atomic blast there. The science community treats these ideas as speculative footnotes, not serious contenders. One more possibility is cryovolcanism or cold eruptions. In settings where frozen water or ice beneath permafrost becomes fluid, pressure might cause explosive bursts. Some geologists point to the Little Ice Age era, when Siberia's climate oscillated. But the volume of rock, structure and heat signatures at Patomskiy are unlike known cryovolcanic forms, so this remains a niche idea. Through decades of fieldwork, labs have built a kind of forensic file. In 2008, geologists Antipin and Fedorov published data concluding that phreatic explosions are the most plausible origin. Their evidence, structural zoning, lack of meteoritical anomalies, isotopic shifts consistent with interaction of fluids and rock, and morphology more like explosion cones than impact craters. Across the concentric rings, chemical variation is gradual, not abrupt, which fits thermal diffusion more than shockwave. Still unanswered are crucial points. What triggered the heat? Was it deep faulting or magma movement? If magma was involved, where did it go? Did multiple blasts build the cone in stages, or was it a single massive event? Why does the central dome remain elevated? What held it in the middle when the surrounding rock blew outward? Another odd feature. The mound seems to shift slowly. Surveys show slight vertical movement and subtle changes in volume over years. The cone is not frozen in stasis. It lives, in a sense, as though the same forces that created it are still whispering beneath. Erosion, permafrost dynamics, internal stress may all still play parts. The local folk traditions add another layer. Indigenous peoples named it Fire Eagle's Nest, warning outsiders that strange forces may dwell within. Some report uneasy sensations near the rim, or that animals avoid the area. Folklore is not proof, but in places like this, even local memory can preserve clues lost to geology. When explorers walk its inner crater, they find shattered limestone blocks, fractures, some chemical staining, but little else. No meteoric debris, no magma glass shards, no metallic cores. The central knoll rises about 12 meters above the crater floor. That mound may be the remnant of rock that resisted collapse. Scientists continue running models. They simulate steam expansion, subsurface fracture networks, and collapsing rock mechanics. They compare crater parameters to known explosion craters and volcanic explosion cones elsewhere. None of the analogues match perfectly. Each matches one aspect while failing another. The deep-time detective in us demands context. This crater may be among the youngest large geological anomalies on Earth. In centuries, soil and vegetation should obscure it, yet the rock is bare, weakly weathered. That suggests it is very young. Yet the tree ring evidence puts episodes of trauma in the early 1840s, possibly hinting the explosion occurred then. Some argue that may mark when one or more blasts occurred, or when the environment shifted. What would it mean if the crater formed in the 19th century? That such explosive geological behaviour can occur in relatively recent times? A reminder that Earth still holds surprises. But if it formed earlier, say 500 years ago, we must ask what climate, hydrology or tectonic environment could permit it. In approaching Patomskiy, each layer is a statement against certainty. Every crater, ridge, fracture adds a voice, but voices contradict. The lab scientists weigh isotopes, map zoning, test trace elements. The field teams measure angles, count blocks, trace fractures. Deep time analysis considers age, erosion, climate shift. What emerges is not a single answer, but a gallery of hypotheses, each with merits and gaps. When the wind laughs across the stone, it carries no consensus. The cone stands patient, unmoved by the arguments swirling its base. For the explorers and scientists left behind, maps, data points and open questions, and so the crater remains a monument to mystery. In the forest, a silent sentinel still waiting for the next clue to break the hush. Lake Baikal's giant ice rings. On a cold winter's day, the surface of Lake Baikal looks like a giant frozen mirror. But toward the end of winter, something odd begins to appear. From space, satellites have captured nearly perfect circular rims carved into the ice. Smooth, concentric rings, sometimes several hundred meters in diameter, appearing against the white expanse. They look too regular to be random cracks, too circular to be wind-driven fractures, and yet they appear, vanish and reappear, with no fully accepted cause. Long before modern observers, fishermen and herders around Baikal sometimes noticed round holes or clear patches in the ice. But only with satellite imaging in the 21st century did scientists realize how widespread and uniform these ice rings are. The NASA Earth Observatory published images showing multiple large rings in southern Baikal during late winter when ice thickness is great, yet still dynamic. The rings' outlines are often razor-sharp. Their edges drop from clear, smooth ice to fractured fissures. The contrast is striking against the otherwise textured ice sheet. Scientists treat these rings as a system puzzle. To explain them requires understanding ice mechanics, lake hydrodynamics, methane behaviour, temperature cycles, and geological undercurrents. They are puzzles not just of cause, but of interplay. What combination of processes can yield such clean, circular features? One of the earliest hypotheses is that eddies beneath the ice, rotating currents in the water, carve them. As ice forms and thickens, slight currents may rub against the base, slowing locally or degrading the ice underside in a ring shape. Over time, the ice edge fractures and forms cracks that align with the current's path. In this view, temperature gradients, wind forcing, and underwater topography all shape the eddies. Indeed, Baikal does have strong internal currents, circulation driven by seasonal changes, thermoclines, and inflow from rivers. Some of these currents hover near the bed in spring, and modelling shows that under certain speed and shear conditions, they could wear ice from beneath in a ring. But that hypothesis doesn't explain all the rings. Some rings appear where hydrodynamic models don't predict strong eddies. Some rings sit over flat, deep lake bottom with little topographic variation. Others show up far from inflow zones or river mouths. The eddy hypothesis can match a few but not the full diversity. Another candidate is the release of methane, gas bubbles rising from the lake bed. Baikal is known for methane seeps and gas discharge from its sediment layers. If large volumes of methane bubble upward, they might thin the ice from below, warm gases rising through fissures, heating and melting it in a ring. Methane bubbles follow fractures and weak zones, possibly creating circular paths if the gas source is ring-shaped or distributed around a circular fissure. Some rings do correlate with known methane vents or tectonic fault lines. In winter, methane rising into cold water may freeze momentarily, then thaw or weaken the ice around the edges, forming sharp circular cracks. Still, methane is not a universal answer. Some rings have no known underlying gas vents. Methane flux may be too weak to affect large ice thicknesses. In many cases, surveys below the ring detect no elevated methane concentrations, no bubble tracks, and no thermal anomalies. In those cases, methane is an incomplete explanation. Thermal stress and temperature gradients offer another piece of the puzzle. Ice expands and contracts with changes in temperature. In large lakes like Baikal, midday warming, nighttime freezing, solar absorption, snow cover variation, and internal conduction create complex stress patterns. In very cold periods, differential expansion may push and pull on ice, leading to cracks that propagate outward. Among these cracks, some might loop back to begin circular fractures. If a small initiation ring occurs by a weak spot, by a gas bubble, or by a freeze crack, stress fields might amplify it into a full ring. In other words, the ring might grow from a small seed via mechanical feedback. This mechanism could supplement eddies or methane effects. Another factor is ice thickness variation. In Baikal, the ice may reach 2 meters or more in deep regions, but might be thinner over upwellings of warm water or shallow slopes. Regions of thinner ice are more vulnerable to melting or fracturing under stress. If a subsurface zone is slightly thinner in a circular annulus, then above it the crack can propagate more easily. Mapping of ice thickness beneath rings sometimes shows depressions or variations. Lake bottom topography also plays a role. Some rings lie over known submerged ridges, submerged slopes, or geological faults. These features may influence water flow, guide eddies, or localize thermal exchange. For example, water upwelling from deep faults might raise heat locally. Rocks near faults may carry different conductivity. Such irregularities can serve as hidden templates on which rings trace themselves. Field studies try to test these mechanisms. Ice cores drilled at ring edges show temperature profiles and microstructure differences versus background ice. Geophysicists use sonar to map the water flow beneath, looking for currents and eddies. Gas probes sample methane concentrations below ring zones and in nearby control areas. Thermal imaging, infrared from aircraft or drones, measures surface temperature gradients morning to night. In some instances, temporary instrumentation monitors ice strain and displacement. In one case, ice cores from a ring edge revealed small air inclusions, unusual micro cracks, and slightly elevated temperatures near the boundary. These signs hint that structural weakness or microfracturing is concentrated at ring edges. In another location, sonar mapping captured a faint rotational current just below the ice, consistent with a weak eddy that might erode ice from beneath. Yet, in a sample area where no methane was detected and water flow was minimal, the ring still formed. That challenges both the methane and eddy models there. Seasonal timing is another constraint. Rings tend to appear when the ice is thick and strong, late winter. If they formed too early, the weaker ice would crack and fail. Too late, melting and snow cover hide them. The timing window is narrow. That helps narrow possible causes. Only mechanisms active late in winter, such as rising lake temperatures or subsurface currents, or gas flow when ice is rigid, are plausible. Moreover, rings sometimes vanish or fragment in a few days. The ice shifts, cracks widen, melting diffuses edges, and snow covers the contrast. Some rings reappear in nearly the same place season after season, hinting at underlying persistent features, perhaps basins, fractures, or vents that recur. These recurrent rings suggest that not all rings are random, some are anchored by structural or geological features. Still, many rings defy patterns. Some are concentric doubles, 2 rings sharing the same centre but different diameters. Others are partial arcs, broken by fractures or ice ridges yet hinting at full circles. Some centres lie in deep water, others closer to shore. Some appear in clusters, others stand alone. The variance forces scientists to think not of a single cause, but of a system of interacting processes, currents, gas dynamics, temperature stress, ice strength, geology and timing. In modelling the system, researchers consider superposition. A methane flux may weaken ice slightly, a subtle sub-ice eddy may increase shear, thermal stress may provide crack guidance, ice thickness variation channels the crack. Together those factors might sum to produce a ring in some locations but not others. In places where one factor is weak, another must compensate, or the ring fails to form. One team used computer simulations combining fluid dynamics, thermal diffusion, gas diffusion, ice fracture mechanics, and lakebed topography. They found that only under narrow parameter ranges do stable rings appear. Too strong a current breaks the ring, too weak and no wear occurs. Too large a temperature gradient causes radial cracks. Too uniform stress yields no pattern. In those models, rings emerge when eddy shear and gas flux are both modest, when ice is brittle but thick, and when the lakebed shape subtly directs flows. Still, these models are sensitive to input assumptions. Water temperature gradients, gas flux rates, bottom topography detail, and ice rheology. Many input data remain coarse. The lake's deep waters are cold but may have internal heat anomalies. Methane seep rates vary seasonally and spatially. The fracture toughness of Baikal ice under extreme conditions is imperfectly known. Hence, modelling yields possibilities, but not certainties. Recent satellite time-lapse studies track ring appearance and disappearance across seasons. Some areas show rings recurring in the same spots year after year, strengthening the idea of fixed subsurface drivers. Others show rings migrating slowly outward or contracting. That motion may reflect changes in water currents, long-term warming or shifts in gas discharge. The data also show that rings tend to intensify, edges deepen in crack width and contrast, before they fade, implying a growth phase followed by decay. Sometimes ring features develop ramps, sloped transitions rather than sharp edges. That suggests gradual weakening rather than abrupt fracture. In other cases, the ring edge is a sheer drop in crack depth. The morphology differences hint that different processes dominate in different rings. Scientists now debate classification. Which rings are eddy-driven, which methane-driven, which stress-crack-driven, and which are hybrids. Some propose mapping rings into types and correlating with subsurface surveys, seismic maps, gas flux maps, bathymetry, and thermal sensors. In effect, each ring is a case study of the system at one moment. The challenge is immense. Baikal is vast, deep, and cold. To monitor ice strain, currents, gas flux, and thermal profiles in many ring sites requires a network of autonomous sensors, expensive and difficult to deploy. Harsh conditions, shifting ice, and remote access hamper field campaigns. Yet small teams do venture out. Drilling rigs, sonar buoys, temperature moorings, gas samplers. Each data point helps sharpen the model. In the end, the giant ice rings of Baikal confront us with complexity. No single cause, but an orchestra of forces. Ice, water, gas, heat, rock, all play roles. Where the balance is just right, a ring appears. Where one factor fails, nothing forms. The rings are ephemeral sculptures in ice. Beautiful, transient, and telling us that even in frozen simplicity, nature's systems dance in layers. Yamal's exploding permafrost craters. In the northern silence of Siberia, a new kind of landscape has begun to appear. Enormous gaping holes in the frozen ground. They seem to appear overnight. Deep vertical shafts surrounded by walls of shattered ice and soil. The locals in Yamal call them Earth's mouths. Scientists call them gas emission craters. The world first saw them clearly in 2014, when helicopter footage revealed a perfect dark pit in the tundra, its rims scorched and fractured, snow blasted outward in every direction. No one knew how it got there. When researchers reached the site, they found a crater about 30 meters wide and 70 meters deep, filled with frozen debris and ice blocks thrown far from the center. Methane levels were off the scale. The walls showed smooth, glassy ice layers interrupted by torn chunks of soil and vegetation. Around the rim, the tundra bulged upward, as if the ground had first swelled, then burst apart under enormous pressure. The smell of gas lingered in the air. Over the next few years, new craters appeared across the Yamal and Gidon peninsulas, dozens of them. Some near river valleys, others in the middle of flat, frozen plains. Each crater seemed to tell the same story. First, a slow swelling mound of frozen earth. Then, a sudden eruption that scattered ice hundreds of meters away. Scientists began to realize that these explosions were not isolated accidents, but part of a process happening beneath their feet. Teams from the Russian Academy of Sciences and international partners arrived with drills, drones, and instruments that could measure gas concentration, temperature, and ground deformation. They camped for weeks in conditions far below freezing, collecting samples from the crater walls and the permafrost below. What they found pointed to an interaction between ice, gas, and rising temperature. Methane was trapped under layers of permafrost, and when heat from above reached certain depths, it triggered a violent chain reaction. The permafrost acts like a thick, frozen lid sealing gas and groundwater below. As the Arctic warms, that lid weakens. In some places, ancient deposits of methane hydrates, ice crystals that trap methane molecules under high pressure, start to destabilize. At the same time, meltwater from the thawing surface seeps down through cracks, pooling in salt-rich layers called cryopegs, where liquid water persists even below 0 degrees Celsius. Those cryopegs create pressure zones, pushing upward as they expand. When gas from the hydrates mixes with that pressure, the ground above begins to lift, forming what scientists call a bulgunyak, a swelling mound that signals trouble. The process is silent until it's not. As the gas concentration rises, pressure inside the mound reaches a breaking point. The permafrost above cannot contain it anymore. When the surface fractures, the release is instantaneous. A massive jet of methane and soil erupting into the air, carving a cylindrical hole in seconds. The explosion throws ice boulders the size of cars and leaves behind a clean, steep-sided crater that slowly fills with meltwater, becoming a lake. Within months, the evidence of violence is replaced by calm, another round pond in the tundra, indistinguishable from the countless others. To understand the sequence, scientists analyze soil chemistry, gas isotopes, and ice layering. Samples show methane with isotopic ratios typical of deep, thermogenic sources, gas formed under high pressure long ago, mixed with biogenic methane produced by microbes. That mix suggests the gas doesn't come from a single layer, but from multiple zones converging near the surface. Some originates from decomposing organic matter, some from deeper hydrocarbon reservoirs that Yamal is famous for. The region sits atop vast natural gas fields, making it a unique laboratory for studying permafrost dynamics and methane behaviour. One of the biggest clues came from satellite images. In some areas, high-resolution data captured subtle changes before the explosions, circular domes rising over months, surrounded by cracks. The bulging ground sometimes measured up to 5 meters high before disappearing in a blast. In other cases, there were no warning signs at all. The variability confused researchers. Why do some mounds explode while others collapse quietly into sinkholes? What exact combination of heat, pressure, gas, and water tips the balance? Field experiments have shown that even small changes in soil temperature can trigger major shifts in gas pressure. A few degrees of warming in the permafrost layer can multiply the pressure in trapped pockets by several times. As water infiltrates frozen ground, it changes its thermal properties, accelerating thaw and increasing stress. The interplay between ice, liquid, and gas is not linear, it's chaotic. Each layer reacts differently depending on its salt content, composition, and porosity. One mound might survive decades, another might erupt after a single warm season. Drone surveys show that many craters are aligned with ancient fault zones and fractures in the bedrock. Those cracks serve as conduits for gas migration, guiding methane upward toward weaker sections of the permafrost. When pressure builds, it follows those paths to the surface. Some craters cluster along these geological lines, hinting that tectonic structure plays a hidden role. In others, hydrology dominates. Water accumulation in thaw zones increases hydrostatic pressure until rupture. Scientists also monitor the craters after they form. At first, methane emission from the newly exposed walls is intense, but over time it declines. The crater gradually widens as ice melts, transforming from a steep shaft into a lake with sloped sides. Vegetation begins to grow along the rim. Within a decade, it becomes just another thermokarst lake, indistinguishable from natural ones, except for the records stored in its sediments and the satellite archives that caught its birth. Instruments placed near active bulgunyaks record slow deformation, millimeters per week, before some events. Gas pressure sensors buried near the base measure increases in methane concentration that rise exponentially in the weeks before explosion. Temperature probes show that these pressure spikes coincide with thaw, reaching deeper than in previous years, but the window of observation is small and many mounds remain unmonitored. The Arctic is vast, access is hard, and the events are unpredictable. Scientists suspect that the sequence is self-reinforcing. As more permafrost thaws, more gas is released. That gas adds to atmospheric warming, which further accelerates thaw. In this feedback loop, explosive craters are the most dramatic outcome, but they are only one symptom. Beneath the tundra, a quieter process unfolds, continuous degassing through cracks and seeps that never explode but still vent methane into the air. Those invisible emissions may contribute more total gas than the spectacular blowouts. Field notes from recent expeditions describe how fragile the balance has become. In some sites, permafrost that once remained frozen year-round is now soft to the touch by late summer. Meltwater collects in shallow pools where tundra used to be dry. Gas bubbles rise through these water, bursting with faint pops. Thermocameras capture warm anomalies even in midwinter, where permafrost should be solid. Each observation adds another layer to the system's puzzle. Temperature, water, pressure, chemistry, all shifting faster than before. Even small details complicate the models. The orientation of the sun, snow cover thickness, and vegetation type influence local heat retention. Moss traps warmth differently than lichen. Snow insulates the ground, slowing freezing in winter. These variations cause localized hotspots that can change where thaw occurs first. In the Yamal Peninsula, such fine differences determine which patch of tundra might explode next year and which will stay silent. Geophysicists studying the crater walls noticed that the lower layers show signs of repeated freezing and thawing. Annual cycles recorded like rings in ice. Each cycle expands the thaw front downward, eroding the permafrost base. The deeper the front reaches, the closer it comes to buried gas hydrates. Once the stability boundary crosses a critical threshold, hydrate ice turns to gas, expanding in volume by more than 100 times. The permafrost layer above has nowhere to go but up. The Yamal craters have become both warning and window. They show how a frozen landscape responds to heat and pressure after millennia of stillness. They reveal how invisible processes beneath the surface can erupt with force capable of reshaping the land. Scientists continue to measure, model, and monitor, trying to anticipate where the next rupture might appear. In the tundra, beneath a crust of ice that once seemed eternal, something continues to stir, silent until it isn't. Khatyrka meteorites natural quasi-crystals, Chukotka. A thin mist clings to the tundra in Chukotka as dawn breaks, and a handful of scientists tread quietly over moss, rock, and wind-scarred earth. They carry delicate tools, microscopes, scanners, electron beams, into the domain of minerals so strange that for decades their existence was doubted. Deep in their pockets, in clean vials, lie fragments of a meteorite unlike any other, Khatyrka. In those fragments lie quasi-crystals, materials once thought impossible in nature. Their story stretches back billions of years, across space and time, and still challenges our understanding of how matter can order itself. The Khatyrka meteorite was found in 2011 in the Yomraut-Vam Valley in Chukotka, in the Russian Far East. Small grains of it, less than a millimeter across, were buried for thousands of years in ancient river sediments. When scientists analysed them, they saw metals, silicates, and an alloy of aluminium, copper and iron. But what caught attention were odd, perfectly symmetric microscopic grains that did not fit any known crystal structure. In those grains, atoms arranged in patterns with five-fold symmetry, which classical crystallography deemed forbidden. These were quasi-crystals. Before Khatyrka, researchers had produced quasi-crystals in the lab, materials that combined order and non-repetition. But whether nature could ever produce them had remained an open question. The grains from Khatyrka offered the answer: yes, nature did, under extreme conditions. The first quasi-crystal identified in that sample was icosahedrite, with formula Al63Cu24F13, named for its icosahedral, five-fold symmetry. Later, a quasicrystal called decagonite Al71Ni24Fe5 was discovered in the same specimen with tenfold symmetry. Subsequent study revealed a third, previously unknown quasicrystal phase as well. To understand how such exotic structures could form, scientists turn their gaze far into deep time and space. They frame a detective story, the meteor's origin, its shock history, its cooling, and how atomic patterns settled. One major insight comes from cosmic exposure data. By studying noble gas isotopes trapped in mineral grains, researchers estimate the asteroid fragment faced cosmic rays for 24 million years, meaning it journeyed through space before arriving at Earth. The meteor experienced a shock event, an impact, at pressures exceeding 5 gigapascals and temperatures above 1,200 degrees Celsius in some zones. Under those conditions, local melting and rapid cooling produced environments where exotic atomic order could freeze in. That scenario aligns with lab experiments. In shock recovery studies, scientists simulate impact conditions, compressing metal alloys with high pressure and temperature, then cooling rapidly. In those tests, they successfully recreate the same Alcoufe quasicrystal phases found in Khatyrka. That strongly supports the idea that natural quasicrystals emerge during impact processes, collisions in space, heat and pressure, then flash cooling that locks atoms into non-repeat ordering. Still, many puzzles remain. The atomic compositions of the natural quasicrystals sometimes lie outside the stability fields predicted by theory and lab experiments. That means that some quasicrystal grains in Khatyrka occupy compositional spaces that did not match lab-grown analogues. That suggests that nature's conditions, cooling rate, pressure path, element supply, may allow phases that were once considered impossible in the lab. In effect, the meteorites have pushed boundaries of material science. Another mystery is how these quasicrystals survived eons of space travel, entry through the atmosphere, and terrestrial weathering. The grains are tiny and delicate. They had to avoid melting, dissolution, or deformation. That implies they were deeply embedded in the meteorite matrix, protected by rock around them, and that subsequent heating was limited. The presence of companion minerals like khatyrkite, a copper-aluminium alloy, cupalit, and other exotic intermetallics hints at a complex metallic assemblage in Khatyrka that may have buffered those quasicrystals. Then there is the question of parent body. Where in the solar system did this meteorite originate? Some investigators point to asteroid 89 Julia as a candidate, based on reflectance spectra that match fragments of Khatyrka. The theory goes that a collision somewhere in the asteroid belt produced fragments, one of which became Khatyrka. That impact may itself have generated the shock necessary to form quasicrystals. In that sense, Khatyrka may carry a fossil record of a collision event in the asteroid belt, preserving exotic minerals that formed, cooled, and travelled across space before landing in Siberia. Geochemists examine trace elements and isotopic systems in Khatyrka to tie it to other meteorite families. Its classification as a CV3 carbonaceous chondrite aligns it with meteorites rich in volatile compounds and metal phases. The fact that only Khatyrka has yielded natural quasicrystals suggests that specific conditions, alloy composition, shock energy, cooling history, must align just so. Not every collision will yield quasicrystals. Many will produce melted metal, recrystallized grains, or disordered alloys. Khatyrka may lie at the edge of what is possible. In tiny fragments, researchers use transmission electron microscopy, electron backscatter diffraction, and microprobe analyses to map atomic arrangements. They see atomic planes doubling back, petal-like domains, and repeating motifs that never exactly repeat, the hallmark of quasicrystals. They compare multiple grains, catalogue differences, test orientations. They find that some quasicrystals are bounded by more conventional metallic phases. For instance, a quasicrystal grain may sit against a khatyrkite grain, or surrounded by stolperite or holosterite. Those associations provide clues to how the metals melted and diffused before freezing into phases. A specific discovery is the I-phase II quasicrystal of composition Al62Cu31Web7. That variant lies outside typical lab stability zones, but matches some of the natural Khatyrka grains. In shock experiments, scientists have now reproduced that phase under controlled conditions. a key breakthrough proving that the I-Phase 2 quasicrystal is indeed producible under realistic impact conditions. That reduces the realm of speculation and reinforces that the meteor's shock pathway is central to the mystery. Still uncertain is the sequence. Did quasicrystals form first, then metallic phases grew around them, or was it reverse? Did the cooling front sweep from one side, creating gradients? Did gas or melt infiltration assist diffusion? Why do only tiny grains survive, and why so few samples ever show quasicrystals? It's possible that many meteoritic fragments once contained them, but subsequent heating or alteration destroyed them, leaving only exceptional cases like Khatyrka as survivors. Deep-time detective work also includes modelling atomic diffusion under shock and cooling, simulation of alloy phase diagrams under non-equilibrium conditions, and computational crystallography to predict possible quasicrystal compositions. Researchers test whether other element systems, not just Alcufae, might support quasicrystals naturally. Recent studies suggest that natural quasicrystals could exist more widely, but remain undiscovered, hidden in meteorites or even terrestrial deposits. Each quasicrystal grain in Khatyrka is a signal in deep time, a record of atomic motion during explosive collisions billions of years ago. But these signals are faint. They're embedded in metal alloys, masked by shock deformation, diffusion, and cosmic irradiation. To read them, scientists must separate sifting noise, alteration, contamination, terrestrial oxidation from the original pattern. That's the detective's challenge. The more the team studies Khatyrka, the more it reveals about material science, planetary collisions, and the boundary between order and chaos in solid matter. But the core mystery remains: how exactly did nature create quasicrystals in space? What precise pressures, temperatures, cooling rates, and chemical environments allow atoms to lock into non-repeating order? And could there be others waiting in meteorites yet undisturbed, waiting to defy our expectations again? The 1908 Tunguska blast. In the pale dawn of June 30th, 1908, the sky above the remote Siberian taiga shifted from quiet to catastrophe. Villagers and Evenki hunters saw a blue fireball streak across the heavens, brighter than the sun, trailing shimmering vapour. Moments later came a flash, a shock wave, and the forest trembling under a force from above. Over the next hours, more than 2,000 square kilometres of fir trees lay flattened, some snapped like matchsticks, others scorched. The blast left no impact crater. The trail it left is a forensic riddle in ice, wood and soil. Decades passed before scientists could truly engage the scene. In 1921 and later, expeditions led by Leonid Kulik, surveyors trekked into the mangled forest, measuring radial treefall, mapping blast zones, and gathering the charred remnants of wood and soil. They reported butterfly patterns, wedges of destruction extending in two lobes from a central zone. They marked a circle of devastation, but in its centre no crater was found. The conclusion? The object exploded in mid-air. That became the dominant model, an airburst. Modern researchers reconstruct the event through a convergence of signals. Tree rings record trauma. Growth anomalies in trees several kilometres away point to a pressure wave. Seismic stations around Eurasia recorded earth tremors. Barometers captured atmospheric pulses. Blocks of wood, charcoal layers in peat bogs, and microscopic mineral fragments hide in soil cores. In short, the clues of destruction stretch from surface damage to microscopic traces. Much modelling has followed. A popular tool is the pancake or fragmentation model. As the cosmic body enters Earth's atmosphere at tens of kilometres per second, aerodynamic pressure flattens or fragments it, increasing its cross-sectional area like a pancake, boosting drag, heating and internal stress until it disintegrates and deposits energy downward. At a critical altitude, often estimated between 5 and 10 km, the remaining mass explodes, releasing energy in a burst rather than impacting the ground intact. That explosion's blast wave travels outward, flattening trees in a radial pattern. The absence of a crater fits. Nothing large reached the surface intact. In recent models, that energy is modelled at between 3 and 5 megatons of TNT equivalent, though other estimates place it as high as 10-15 megatons. Still, disputes linger. The airburst models must explain how shock, heat and winds strong enough to fell trees tens of kilometres away could occur without melting or igniting all wood. Some studies argue that temperature and wind effects projected by certain models are physically impossible under air blast conditions. In a 2025 paper, Boslow and colleagues questioned earlier assumptions, arguing that the claimed temperature and wind speeds at some distances cannot be produced by a pure airburst at modelled altitudes and energies. That challenges parts of older reconstructions. One major debate centres on Lake Checo, about 8 kilometres north-northwest of the putative epicentre. In 2007, Italian scientists proposed that Checo is a small impact crater left by a fragment surviving the airburst. They measured bathymetry, saw a bowl shape, and recorded seismic and magnetic anomalies beneath the lake bottom. Some claimed the long axis of the lake aligns with the blast centre. They suggested sediment cores showed younger lacustrine deposits, consistent with formation around 1908. That would imply the extraterrestrial body left one piece that struck and formed a small crater in permafrost. But critics counter hard. One study argued that sediment accumulation rates and core stratigraphy show that Checo is much older, hundreds to thousands of years older than 1908. Trees around the lake rim are older than 100 years. Morphologically, the lake lacks the classic ejector signatures of an impact crater. Magnetic anomalies could arise from deep rock variations. Some recent Russian studies discovered other similar funnel-shaped lakes near the blast zone, suggesting Checo's shape is not unique. The presence of multiple crater-like lakes in the area complicates the assignment of Checo to the 1908 event. Also, calculations of the strewn field for surviving fragments place Checo outside the most likely fall zone, making it unlikely to be a fragment crater, unless trajectory assumptions are stretched. In further reconstructions, researchers simulate fragment ablation, trajectory, fragmentation, and dark flight. One study computed that macroscopic fragments surviving the airburst could fall roughly 11 kilometers northwest of the center, but Checo lies some distance outside that most probable zone, about 3.5 kilometers beyond a 3 sigma boundary in that model. That weakens the Checo impact hypothesis under standard trajectory assumptions. The forensic record also tries to identify shocked minerals or meteoritic fragments in the blast zone. Some tiny grains of nickel or silicate fragments have been found in peat cores. In tree resin, microparticles show signs of high pressure, yet no large chunks of the cosmic body survive. That absence is consistent with a full disintegration in the atmosphere, but it also robs us of the smoking gun sample. Some researchers, like Rubtsov, have argued that the known evidence does not fit neatly with an asteroid or comet core model, and perhaps the cosmic object belongs to a class not yet well understood. In the chronological reconstruction, the following timeline is commonly accepted. The object speeds into the atmosphere at tens of kilometers per second. At altitudes perhaps between 10 and 15 kilometers, or lower under some models, it begins to fragment and flatten under pressure. At a critical point, internal stresses or thermal disruption trigger a rapid decompression explosion. The resulting blast wave cascades down into forest, producing wind, heat, and overpressure that flatten trees radially. The shock then propagates outward across plains, triggering secondary breaks far out. Meanwhile, small fragments may have survived, but none large enough to make typical crater structures, unless Checo is one. Newer work reviews which aspects of damage the models can reproduce. High-fidelity simulations attempt to recreate treefall patterns, pressure gradients over distance, the butterfly footprint and thermal effects. Some align well, other predicted thermal or wind intensities exceed what tree charring and fire evidence support. That suggests that models may overestimate energy coupling or misplace altitude of explosion. The precise angle of entry and object composition affect fragmentation behavior. A stony asteroid behaves differently from an iron or comet fragment. The lack of volcanic or tectonic origin strengthens the extraterrestrial hypothesis, but which kind remains uncertain. In recent decades, scientists have also revisited peat bog records near the centre. Some cores contain layers with elevated platinum group metals, microspherules, and anomalies consistent with extraterrestrial dust deposition around 1908. Tree rings in regions beyond the blast show growth suppression or reaction at 1909, hinting at atmospheric effects. Some reports describe nights in Europe glowing red in summers after the event, possibly from high-altitude dust similar to volcanic hazes. Those signals strengthen that material reached upper atmosphere, beyond just forest destruction. Yet, when models attempt to connect upper atmospheric signals to ground effects, mismatches appear. Some predicted dust mass and altitude needed to explain sky glows or pressure waves exceed what realistic fragmentation models yield. That again raises calibration tension. No single reconstruction yet matches every known datum: treefall, shockwave, thermal damage, microdebris, fragment distribution, and possible crater traces. Even now, small expeditions probe Lake Checo sediments, sample magnetic anomalies, and map subaqueous structure. Some suggest a meter-sized chunk of rock lies buried beneath the lake, but no consensus emerges. Field teams across seasons coring deeper sediment layers, refining radiocarbon dates, and comparing with regional lakes to test uniqueness. Tunguska remains a forensic maze: wood patterns, shock waves, atmospheric records, microscopic particles, and a lake that may or may not record an impact. Its personality is many-faceted: explosion without crater, debris without body, modelled power that sometimes overshoots observed effects. We still don't know exactly what the sky object was: asteroid, comet, fragment, or something stranger. Yet each reconstruction gets us closer to unravelling a morning in 1908 when the forest fell silent under a cosmic voice. Denisova Cave, a ghost lineage in the Altai. A cold wind whispers outside the dark mouth of the cave in the Altai Mountains, where stone walls hold shadows older than memory. Inside Denisova Cave, every bone fragment, every chipped flint blade, every grain of sediment is a witness to the passing of old human lineages. This is not a site of famous skeletons or grand tombs, but a quiet archive of DNA and of lives lived, interwoven, vanished. When scientists first extracted DNA from a fingerbone here in 2010, the results shocked the world. The genome belonged to neither modern human nor Neanderthal. It belonged to a new group, what they call the Denisovans. That one tiny bone changed the map of human ancestry. From that signal, researchers began to trace a human odyssey tangled with mysteries. The archaeology of the cave is subtle and complex. Excavators have identified more than 20 fossil and artifact layers over 500,000 years. Flints, animal bones, hearth remains, ochre. These show usage by hominins again and again, but rarely long occupation. In the deepest levels, the traces are faint. Higher levels betray more complex tools and ornamentation. It is in those higher layers that researchers found tiny fragments of bone and tooth, enough to extract mitochondrial and nuclear DNA. The Denisovan individuals are known from only a few fragments: a pinky bone, Denisova 3, molars, Denisova 4-8, and small chips whose attribution relies purely on DNA. Out of these, only Denisova 3 yielded a genome of high quality, offering a window into the genetic identity of this hominin. Genetic analysis showed that Denisovans and Neanderthals share a common ancestor, but that Denisovans diverged as their own branch. That branch then interbred with Neanderthals, and also with ancestors of modern humans. In living people today, particularly in Melanesia and parts of Southeast Asia, you can still find 4–6% Denisovan DNA, a living echo of long ago mingling. Perhaps the most astonishing discovery from Denisova Cave is Denisova 11, known in scientific circles as Denny. A small bone fragment from the cave turned out by sequencing to belong to an individual whose mother was a Neanderthal and whose father was a Denisovan. This first-generation hybrid signals that these groups not only met but mated, and in an era when such crossings were not rare but possibly part of life in Ice Age landscapes. To understand the human story here, researchers dig into sediment DNA too, bits of mitochondrial DNA preserved in layers where no bone survives. From hundreds of sediment samples, scientists have recovered Denisovan and Neanderthal genetic signatures, even in strata with no visible fossils. That shows that hominins passed through or occupied the cave in intervals when no bones remain. Indeed, some sediment layers dating 250,000 years ago carry Denisovan signatures. Later, between 130,000 and 80,000 years ago, only Neanderthal DNA appears. Then Denisovans return in later times. These shifts suggest periods when one group held sway, or when populations migrated through. One narrative emerging is this: the first Denisovans reached the Altai region perhaps 300,000 years ago. They lived, moved, and declined in cycles, leaving gaps. Neanderthals moved in or overlapped at times. Then Denisovans return with new mitochondrial lineages, suggesting different populations or migrations from elsewhere. Their presence seems to ebb and flow in response to climate, geography, and opportunity. What remains mysterious is the full range of Denisovans. Although they are named from Siberia, their genetic legacy reaches far into Asia. Work on other caves in Laos, Tibet, and China uncover Denisovan traces. The Denisovan jawbone from the Tibetan plateau suggests they had adapted to high altitudes. In Laos, fragments bear Denisovan affinities. In Taiwan, teeth have hints of Denisovan proteins. These distant footprints suggest their range extended well beyond the Altai. But no full skeleton as complete as the finger bone has yet emerged outside Denisova. We also puzzle over the disappearance of Denisovans. Why did they vanish while Neanderthals and modern humans survived longer? Climate shifts may have squeezed populations. Interbreeding with Homo sapiens may have absorbed their genes into our ancestors. Their low genetic diversity seen in the Denisova 3 genome suggests population bottlenecks or isolation. Their habitats may have been fragile. The evidence pulled from Denisova Cave is one of the few windows we have on their rise and possible decline. At Denisova, stone tools found alongside fragments carry both archaic and modern traits. Some blades, ornaments, and bone pendants point to cultural innovation. It is clear that Denisovans were not primitive wanderers. They made tools, used pigment, crafted jewellery. They were part of the human story, not on the periphery, but entwined with other hominins. One chapter still resists closure. Exactly when Denisovans left Denisova Cave, or whether they lingered longer on its fringes. Some sediment DNA suggests Homo sapiens may have entered the picture in later layers, but no modern human bones have been found in the cave. Whether Denisovans survived until 30,000 years ago in Siberia, or withdrew earlier, is still under debate. Their hybridization with Neanderthals raises deeper questions. How often did this happen? Did hybrids live full lives or lie hidden in signals? Did interbreeding confer adaptive advantages in harsh climates? The genes Denisovans passed to modern humans include those involved in immune response and altitude adaptation, especially in Tibetan and Himalayan populations. Their losses may be part of their survival. In Denisova's quiet chambers, DNA fragments speak of population turnovers, thresholds crossed, climatic stress, mingling, migration, and disappearance. The cave itself holds no voices, only stones and dust. But each sequenced base pair, each molar fragment, each sediment layer is a whisper of their odyssey, and a reminder that in Siberia's vastness, lost human lineages once lived, moved, loved, and left their mark on our genomes. Zhokov Island sled dogs, high Arctic. A cold wind scrapes across the tundra around Zhokov Island as archaeologists peer through snow and ice toward the faint outline of old campsites. This island, remote in the new Siberian archipelago, is a place where humans and dogs forged an early Arctic partnership, one that hints at how sled technology may have begun over 9,000 years ago. Around 9,000 years ago, people lived on Zhokov, hunting polar bears, reindeer, and sea mammals, making tools of bone, ivory, and stone. Among their remains, far more than incidental, are the bones of dogs, canine remains that now suggest deliberate breeding and use in hauling. Field teams first uncovered the site in the late 20th century, exposing tent rings, hearths, bone deposits, and tool caches. Dog bones were mixed in. In later excavations, researchers carefully mapped skull fragments, limb bones, and teeth. Each specimen was catalogued, measured, and compared to modern wolf and dog metrics. The shape of skulls, the robust limb bones, and proportions unlike wild wolves hinted strongly at domestication. That raises the question, were these dogs simply companions, or were they working animals? Detailed morphological comparisons found two size classes among Zhokov dogs. Some were medium-sized, lean, around 20 to 25 kilograms, ideal for pulling loads without overheating or fatigue. Others were larger, stronger types, closer to weights favoured for big game assistance or hunting. This division suggests that ancient people were already differentiating canines by purpose, draft versus hunting, but bones alone cannot prove use. The next step came from ancient DNA work. In 2020, researchers sequenced the genome of a Zhokov dog dated to approximately 9,500 years ago. To everyone's surprise, the genome clusters with modern Arctic sled dog lineages, the Greenland sled dog, Siberian husky, and related breeds. That genomic continuity suggests that the sled dog lineage is ancient, not a recent invention. The genetic signal implies that the dogs on Zhokov already carried alleles adapted to high-fat diets, cold tolerance and endurance. In effect, the dogs had evolved traits suited for labour in the Arctic environment. Still, having draft-capable dogs doesn't prove sled technology. Archaeologists also found wood artefacts, small sled runner fragments and rods, that could belong to sled frames or hauling gear. These pieces are scant and fragmentary, but their presence in direct association with dog remains adds weight to the notion that people on Zhokov were using dogs for transport across ice and snow. Field labs examined bone wear, muscle attachment sites, and joint surfaces. In working animals, repetitive load-bearing leaves telltale marks, robust entheses, smoother joint surfaces adapted to stress and anisotropic growth. Though the methodology is still new for dogs, early studies suggest Zhokov dog bones show more robust muscle attachment than expected in wild canids, consistent with repetitive physical use. Another intriguing line of evidence comes from paleofeces, frozen dog droppings preserved in permafrost. In these samples, scientists detected remains of polar bear fur, reindeer meat and fish, indicating that these dogs ate a high-protein mixed diet. The presence of polar bear fur is surprising, since that prey is dangerous. Feeding dogs leftovers from game may reflect their role in the hunting economy. The diet also carried parasites, tapeworm eggs common when eating raw fish or meat. That indicates they weren't heavily processed or cooked, but fed directly as scavengers or utilitarian animals. The buried droppings also show seasonal patterns. In winter months, more meat remains appear. In warmer periods, fish residues and parasites appear more often. That suggests seasonal shifts in feeding regimes, perhaps aligning with human hunting strategies. Dogs had to adapt diet and metabolism to harsh cycles, part of their training. In reconstructing the human side, archaeologists note that Zhokov's climate is extreme, cold, windy and icebound much of the year. Moving across sea ice or between islands would require efficient transport. Human carriers wearing snowshoes or sledges pushed by people would be heavy and slow. Dogs pulling small sleds would multiply human mobility, enabling transport of meat, tools and raw materials. In that context, specialized sled dogs would be strategic assets. Comparative genomic analysis also suggests gene flow from Pleistocene wolves into early sled dog lines, but the Arctic lineage diverged by about 9,500 years ago, after which admixture with wolves declined. That timing corresponds to the era of Zhokov occupation and suggests a stable breeding lineage. In other words, by Zhokov times, sled dog ancestry had already solidified. The ancient Zhokov dog is not a stray or feral wolf, but a true example of early domesticated working dog. Still, uncertainties remain. The wood sled fragments from Zhokov are small and incomplete. They don't form complete runners or frames. Alternative explanations could tie them to hunting gear, scaffolding, or transport drums. The absence of preserved harnesses or collars leaves open the question of how dogs were hitched or configured. Also, the work stress markers in bones are suggestive but not definitive. Skeletal interpretations vary, and while genome clustering is clear, it doesn't specify exactly when sled use began. Models simulate what sled transport would involve: modest loads, micromoles of friction, gait cycles, rest periods. In cold, snowy terrain, optimal dog weight, harness design, and runner materials all matter. By comparing experimental reconstructions using modern sled dog parameters with Zhokov terrain and drift ice, some models suggest that a small sled pulled by 5 to 8 dogs could carry meat and tool loads efficiently across sea ice between hunting zones. In human odyssey terms, Zhokov stands at a hinge, a point when Arctic peoples may have shifted from foot-based hunting to threshold sled-based economy. That shift would let them extend foraging ranges, revisit isolated sea ice zones, and manage larger game beyond human carry capacity. Dogs may have enabled year-round mobility and shaped human settlement patterns in the high Arctic. Yet exactly when sled technology first appeared remains unclear. Zhokov is our earliest candidate with strong support. Other Siberian and North American Arctic sites post-date it, often showing dog remains but little direct gear. The gap lies in details: how sleds evolved, harness designs, gear materials, and the gradations of use from light pulling to heavy load sledding. Zhokov gives us a window, but not the whole view. By combining bones, DNA, wood fragments, droppings, and modelling, scientists reconstruct a human-dog partnership in Arctic frontier. It was a relationship of companionship, labour, adaptation, and survival. On the windswept ice of Zhokov, humans and dogs stepping side by side began a tradition that would echo across Arctic lifeways for millennia. Jana RHS, people in the Arctic during the last ice age. A cold, pale wind sweeps across the banks of the lower Jana River, and beneath the permafrost lies a secret, a human foothold far north of where people were once thought to dare live. At Jana Rhinoceros Horn Site, or Jana RHS, archaeologists uncovered evidence that, some 31,000 to 32,000 years ago, humans made camp in the Arctic. They hunted mammoths and rhinoceros, made tools, carried ivory, and adapted to polar extremes. Their story remains incomplete, but it stretches our map of human reach in the Ice Age. In 1993, a geologist named Mikhail Dashzerin found along the Jana a slender foreshaft carved from woolly rhinoceros horn. That find lay hidden in riverbank sediments, thawed by erosion, and hinted at something unexpected: ancient people pushing their range far north. In 2001, Vladimir Petulko and colleagues began formal excavations, revealing a complex of 6 loci across a 500 square metre area. The site lies north of the Arctic Circle, around 71 degrees N, on an alluvial terrace above the river's left bank. The cold preserved many bones, tools, and ivory artefacts. Radiocarbon dates, later calibrated, place human occupation between roughly 31,600 and 32,000 years before present. That timing lies before the last glacial maximum, in a period of colder glacial expansion. Yet, the cultural layers at Jana contain a wealth of remains: thousands of animal bones, ivory rods, carved foreshafts, bone and antler tools, beads, pendants, and stone flakes. The diversity of species hunted is exceptional: mammoth, woolly rhinoceros, bison, horse, reindeer, brown bear, hare, fox, muskox, and more. The economy was broad, not narrowly specialised. Human remains are rare. 2 milk teeth from young males were recovered, enough to yield DNA. Genetic analysis led scientists to define a new lineage: ancient North Siberians, ANS. The genomes from these teeth show that ANS derive from an early West Eurasian branch, with a component of East Asian ancestry, about 22%. The Y chromosome haplogroup was P1 and mitochondrial type U. These people persisted in northeastern Siberia and later contributed to gene pools in Siberia, the Americas, and North Eurasia. From a human odyssey perspective, Jana RHS challenges previous models. Before its discovery, many believe the far north was colonized only after glacial retreat, perhaps no earlier than 20,000 to 18,000 years ago. Jana shows that humans pushed into high latitudes far earlier, adapting to harsh cold climates long before the ice sheets retreated. That suggests mobility, flexibility, and technology greater than assumed. But how did humans live there? The system puzzle lies in how climate, resources, technology, and human behaviour interlocked. The Arctic at that time was cold, dry, and exposed. Vegetation zones retreated south. Ice sheets blocked many routes, but some corridors, along river valleys, coastal margins, or refugia, remained open. In the case of Jana, the valley of the Jana River provided a northward route from interior Siberia. Rivers may have served as migration highways, while periglacial landscapes offered seasonal lakes, mammoth-rich floodplains, and patches of tundra flora and fauna. The human groups occupying Jana had to manage thermal stress, food scarcity, seasonal changes, and technical demands. Their tools reflect that. Stone tools at Jana are mainly flake-based, with scrapers, chisels, side tools, but blade tools and microliths are rare. They made foreshafts from mammoth ivory and rhinoceros horn, tips carefully beveled. These shafts may have carried stone or bone points, enabling flexible hunting strategies against large game. The presence of drilled ivory beads, pendants, and engraved tusks shows symbolic behaviour, not just survival. Bone technology dominates hunting instruments. The scarcity of lithic hunting tools, stone points, led to the idea that the people relied heavily on organic toolkits: ivory, antler, bone. That places special demands on mechanical strength, homogeneity of materials, crafting skill, and maintenance strategies. In a region where wood is scarce or patchy, bone and ivory become crucial supply materials, not luxuries. Stable isotope analyses and faunal patterns help reconstruct seasonal strategies. Many animals hunted, reindeer, bison, mammoth, exhibit seasonal migrations. People likely followed those movements, shifting camp between winter and summer zones. Fish or aquatic resources may have supplemented diet in warmer months. The presence of hair remains fully articulated suggests seasonal small game hunting, possibly for fur rather than meat. That emphasis hints that clothing, warmth and insulation may have mattered as much as calories. The symbolic objects and beads suggest social networks, alliances, exchange lines, and perhaps seasonal aggregation with other groups, but climate variability, cold stress, daylight extremes, and resource unpredictability required resilience. The system puzzle forces us to consider feedbacks. A weak summer might reduce prey availability, a harsh winter might push a camp towards starvation. People may have timed occupation windows, retreated during the worst conditions, or maintained supply caches. Mobility was likely modular and responsive. Researchers also examined spatial geometry of Jana loci, mapping hearths, artifact scatters and refuse zones. That helps estimate camp layout, activity zones, and site reuse patterns. Sediment micromorphology and microstratigraphy show hearth layers and trampling signatures. Bone fragmentation patterns tell whether animals were butchered on site or partly processed elsewhere. In some layers there is burned discoloration, ash lenses, burned bone, showing fire use in a cold environment. That indicates fuel procurement, fire maintenance and site planning. Paleoclimate proxies rain from ice cores, pollen records, and low-S sequences around Jana. At 31-32 K, the climate was cold, with lower oxygen isotope values, sparse tree coverage to the south, extensive permafrost, and limited summer warmth. However, irregular warming pulses may have temporarily allowed more lush vegetation or open water corridors. These windows likely determined when groups pushed into the high latitudes. Human presence at Jana may coincide with interstadial warming periods, when conditions eased for months or decades. Modelers build demographic simulations coupling climate reconstructions, prey densities, human energy budgets, and carrying capacity. In some models, small bands of 20-40 people can persist if mobility is high, diets are flexible, and seasonal territories overlap. In others, population crash is inevitable unless fallback zones exist. Jana may represent a frontier zone, occupied during favourable periods, vacated during glacial maxima. Jana's role in the peopling of the Americas also features in system thinking. The ANS lineage may have contributed to the ancestry of Native Americans, either directly or through admixture with Siberian populations. The timing of northward expansion, isolation through glacial phases, and migration down Beringia corridors interacts with what Jana reveals. The ancient northern presence may have paved stepping stones for later eastward and westward migration. But many puzzles remain unresolved. Exactly how long Jana was occupied, continuously, seasonally or episodically, is unclear. Whether the people left in harsh cold phases and returned is debated. The nature of social structure, group size, intergroup interaction and mobility pattern is speculative. The degree to which these people exchanged with or influenced populations to the south is also unknown. The more scientists sample sediment DNA, paleoclimate records and artifact layers, the more dynamic Jana becomes. Not a static outpost, but a living node in Ice Age networks. The caveat is always taphonomy. Permafrost shifts, sediment mixing and erosion distort the record. The site may represent the most robust signal we have of Arctic settlement, but it may omit innumerable ephemeral camps lost to time. At Jana, bone and ivory tools lie quiet in frozen soil, teeth whisper of genetics long dispersed, animal bones speak of prey and climate. In this human odyssey, the northern frontier was not an afterthought but part of the adaptive expansion of our species. Systems of tool, diet, movement, climate and genetics wind around Jana's story, as if told by a fragile network of trails across ice, between warm seasons, across millennia, Ust Ishim, West Siberia. Long before modern maps laid their lines across Siberia, a single bone lay quietly eroding out of an alluvial bank of the Irtysh River. In 2008, a sculptor named Nikolai Peristov spotted it, a thick, fossilized femur partially exposed by wind and water. He showed it to a local expert, and soon it was clear. This was human. The bone came from a man who walked that land some 45,000 years ago. He came to be known as Ishim Man, and his story reaches deep into the tangled roots of modern human history. The context was rough and simple. The femur lay in Pleistocene river gravels in a region now in Omsk Oblast, western Siberia. Sediments around it date between 30,000 and 50,000 years ago, making its layer plausible for that time. Radiocarbon dating refined its age to roughly 45,000 years before present, placing it among the oldest known and anatomically modern humans whose DNA we can study. Guided by careful excavation and geologic survey, scientists removed the bone, cleaned it, and preserved it. In the lab, the bone's shape told part of the story. Its shaft is robust, the muscle attachment regions pronounced, and its cross-section falls within the variation of Upper Paleolithic modern humans rather than Neanderthals. Its anatomy marks it as someone fully human, Homo sapiens, but from a time when the world's human map was still being drawn. The real revolution came when researchers extracted and sequenced its DNA. The genome was of extremely high quality for such antiquity, and it showed something astonishing. This man carried Neanderthal DNA, about 2 to 2.3% of his genome, similar to what many modern non-African populations carry today. But the Neanderthal segments in his genome are much longer than those in modern humans. That means fewer generations had passed for them to break apart. The length of those segments allowed scientists to estimate that Neanderthal gene flow into our ancestors occurred roughly 52,000 to 58,000 years ago, 7,000 to 13,000 years before Ishim lived. That genetic timestamp anchors one of the thickest knots in human prehistory. It places Ishim close to the era when modern humans and Neanderthals were mingling, before later human populations diluted or fragmented those signals. He stands at a branching point, after the interbreeding event but before most of the reshuffling that followed across Eurasia. From a human odyssey perspective, Ishim is a bridge between worlds. Genetically, he's equidistant from later Europeans and East Asians. In other words, he shares common ancestry with both lineages before they diverge sharply. That makes him a representative of a population that straddled that split. A population that may have been ancestral to both Western and Eastern Eurasian families. Alternatively, he may represent a lineage that left no direct modern descendants, one that persisted briefly, as many early human waves did. His Y chromosome belongs to haplogroup K2, a deep lineage whose descendants spread across Eurasia. His mitochondrial DNA is in haplogroup R**. These lineages are found broadly in modern Eurasian populations, but the specific variants he carried are not clearly represented today. That suggests that while his lineage contributed genetic material, his lineage itself may not have persisted in unbroken descent. In reconstructing his wider footprint, researchers compare him to other ancient humans. He sits temporally between fossils like Tianyuan man in China, approximately 42,000 years ago, and later Siberians like Malta boy, MA1, approximately 24,000 years ago. His genome is more closely related to those East and West Eurasian branches than to more ancient African lineages. That pattern supports a model where modern humans spread into Siberia relatively early and then diversified. Yet his genetic closeness to later populations is limited. He does not carry substantial genetic heritage in many modern groups. Some models place him as part of the initial Upper Paleolithic IUP wave, an early expansion of modern humans across Eurasia more than 45,000 years ago. That wave may have left limited legacy, replaced or absorbed by later migrations. In this framing, Ishim represents a deep branch from a wave that radiated out but left few descendants. One major question is, what lifestyle did Ishim's people lead? The bone itself gives no clues of tools, culture or diet, but its geographic position invites inference. Western Siberia, near the Irtish, would have been a corridor between Central Eurasia and Siberian lands. A human living there 45,000 years ago must have moved adaptable tools, diets and strategies. The climate then was cold, periglacial, with fluctuating flora and fauna. Surviving required flexible hunter-gatherer strategies. In the systems puzzle surrounding Ishim, environment, migration, population dynamics, and genetic admixture interplay. As modern humans pushed northward, They encountered Neanderthals. Interbreeding occurred, leaving genetic traces. Some populations moved on, others homogenized, others died out. The effect is a mosaic. Ishim shows a path of human movement and mixing, but not a clean linear line to us. Scientists refine mutation rates using Ishim's genome. Because we know the bone's date, researchers can measure how many new mutations have accumulated in the human lineages since. From this, they estimate a human autosomal mutation rate between 0.4 and 0.6, or a call 10 to 9 per site per year. That helps calibrate molecular clocks used across human evolutionary studies. His genome becomes a temporal anchor, allowing better dating of other events. Another puzzle is why his lineage left limited legacy. Perhaps his group dwindled or later migrations overran them. Later populations in Siberia, such as ancient North Siberians, ANS, or ancient North Eurasians, emerged and reconfigured demographic maps. The genetic signals from Ishim may survive faintly but not dominate. It's possible his population was peripheral or small, enough to contribute genes but not persist in a large branch. Moreover, Ishim teaches us that human spread across Eurasia occurred earlier than once assumed. His presence in western Siberia 45,000 years ago suggests that modern humans crossed vast distances into cold remote lands early in their dispersal. The idea that modern humans waited for warming waves to colonize the north yields to evidence that adventurous bands reached the interior early, but many uncertainties remain. We do not know what tools he used, what language he spoke, how many people were in his group. We do not know how long he or his people lived near Irtish, or where they moved next. It is uncertain whether any part of his line carried into later populations. His is a single femur in time, a window, not a panorama. To expand beyond him, scientists compare others like Tianyuan, Malta, Jana, and ancient Siberian fragments. They look for shared alleles, overlapping ancestry blocks, and migration corridors. These comparisons help position Ishim's group in the human network of ancient Eurasia. Thus, Ishim man is both a human journey and a trace in a system of population movement. His bone bridges the migration from Africa into Siberia, the pulse of Neanderthal mixing, and the branching of human lineages. In his silent femur, the Odyssey of us carries echoes, the interweaving of genes, migration, survival, and the fragile pathways by which Homo sapiens came to inhabit the farthest reaches of Earth. Malta Boy. May 1, near Baikal. A thin mist drapes over the forest near Lake Baikal as researchers step gently across the bones of the past. Near the village of Malta, in Irkutsk Oblast, a child's skeleton unearthed in the early 20th century would, many decades later, shift how we see human prehistory. This child, known as Malta Boy or MA1, lived some 24,000 years ago. His genome holds clues linking Siberian hunters to the first Native Americans and questions about how populations spread, mixed and moved across Ice Age Eurasia. The site itself, part of what archaeologists call the Malta Beret culture, lies roughly northwest of Baikal. Excavations revealed semi-subterranean dwellings, hearths, flint tools, bone and ivory artifacts, and portable art, small figurines carved in mammoth ivory, animals and human forms among them. These finds show a sophisticated, mobile people thriving in harsh Pleistocene landscapes, far from temperate refuges. The skeleton of the boy was first discovered in the 1920s by Russian archaeologist Mikhail Gerasimov, who returned several times to expand the excavation. The child must have died at an early age, yet his burial was accompanied by rich grave goods, ivory beads, pendants, and carved objects. His remains were stored in museum collections until modern scientists could apply ancient DNA methods. In about 2013, a team led by Esker Villerslev and David Reich sequenced the boy's genome, a remarkable technical feat given its age and the degrading effects of time. What emerged was a picture that both affirmed and reshaped models of human migrations in Eurasia and the Americas. Genetically, Massachusetts, one does not cluster closely with East Asians despite being in Asia. He shows strongest affinities with Western Eurasians, hunter-gatherers from Europe and Western Asia, but at the same time, he shares substantial genetic ancestry with modern Native Americans. In fact, the team estimated that between 14 and 38% of Native American ancestry derives from a population related to MA1. That indicates that a component of Siberian DNA, carried by people like MA1, flowed into the ancestors of Native Americans sometime after the divergence from East Asians. MA1's mitochondrial DNA, mtDNA, fell into haplogroup U, found in European hunter-gatherers. His Y chromosome belonged to a basal lineage of haplogroup R, an ancient branch that would later give rise to many lineages in Europe and Asia. These uniparental markers show that his lineage shares deep roots with Eurasian hunter-gatherers, not just local Siberian groups. In terms of human odyssey, Massachusetts, one anchors the ancient North Eurasian component Aenis, a genetic lineage distinct from both European hunter-gatherers and East Asians. Populations like MA1 are considered part of a wider network that spanned Siberia and contributed genes to later groups in Central Asia, Europe, and the Americas. In Siberia itself, after MA1's time, other individuals like those from Afontova Gora show similar Aenis signatures, pointing to a continued presence of this lineage long after the last glacial maximum. Yet many questions remain. We do not know the size of the MA1 population, its territorial range, or how stable it was. Was MA1 part of a small isolated group? Or was he a member of a larger network spanning Siberia? Did people like MA1 migrate seasonally? How far did they roam? The archaeological record gives hints. Tools, dwellings, and art suggest mobility, exchange, and contact. The genetic signal to the Americas suggests connection zones, perhaps in northeastern Siberia. Another puzzle is how MA1's population interfaced with others. The admixture into Native American ancestors must have happened after their split from East Asians, perhaps in northeastern Siberia or Beringia zones. That raises models where migrating East Asian-related groups met descendants of MA1 or ANE populations and mixed, producing the gene pool of first Americans. Whether that mixing was abrupt or gradual, localized or broad, is contested. Climate and environment add another dimension. Around 24,000 BP, the world was approaching the coldest phase, the last glacial maximum. Siberia was cold, dry, with expanded permafrost, limited forests, open mammoth steppe landscapes. Like earlier populations, Massachusetts, one's people had to adapt to resource fluctuations, seasons, and mobility. Constraints, their toolkits, ivory, bone, stone, art, reflect use of available materials and long-distance networks for raw materials. Models attempt to trace how groups carrying ANE ancestry might have spread eastward and northward. Perhaps populations like MA1 moved east along river corridors, through Lake Baikal basins, then toward northeast Siberia. Others could have veered north toward Beringia. Each incremental movement may have left genetic traces in small populations, some surviving, many disappearing. The spatial distribution of ANE in modern Eurasia as a cline supports diffusion from a Siberian core. Archaeologists also examine the material culture for signs of exchange or contact. Some types of ivory figurines at Malta resemble artistic styles seen in Upper Paleolithic Europe, raising the possibility of cultural connections or parallel invention. But such comparisons must be cautious. Similarity does not prove contact, especially in mobile hunter-gatherer art traditions. Another branch of inquiry involves effective population size. Genetic diversity in MA1 suggests that his population was not extremely small. There was enough variation to sustain some lineage, but bottlenecks, climate shifts, and glacial barriers may have constricted the population during harsher periods. During the last glacial maximum, many northern populations contracted or retreated. How the ANE group survived, dispersed, or fragmented remains part of the mystery around MA1's broader footprint. Today, researchers compare MA1 with temporally and geographically spaced genomes. Jana RHS individuals, Ishim, Afontova Gora, and later Siberian groups. Through admixture models, they estimate ancestry proportions, dates of admixture, and branching events. MA1 frequently emerges as a key node connecting West Eurasians, Native Americans, and Siberian lineages. One constraint is resolution. MA1's genome is relatively low coverage compared to modern samples, and post-mortem damage affects interpretation. The further back in time you go, the harder it is to untangle continuous migrations from discrete pulses. Also, many prehistoric populations left no genetic trace because they died out or were absorbed. MA, the 1st of May, represent a ghost lineage whose broader network is underrepresented in samples. He may have had siblings, cousins and neighbours whose remains we simply have not discovered or whose DNA failed preservation. Another open question: did Ma1's group interact with Neanderthals or Denisovans? Genetic analysis shows no strong signature beyond what other modern humans carry, so no major admixture is evident. But in regions of Siberia, repeated contact between hominin groups may have been possible. As scientists explore more Siberian sites, they look for individuals with similar or variant ANI ancestry. Each new genome may reveal stronger continuity or reveal missing links. In time, the map of human migration in northern Eurasia may show networks radiating around MA1's time, linking Europe, Siberia, and the first Americans. Malta boy lies silent under museum lights, but his bones, combined with artifacts and genetics, echo a journey across glacial landscapes. In him, we see a lineage that, reaching deep into Siberia, also reached across continents. His story is a thread in a web of human movement, in which Siberia was not the end of the line, but a crossroads among paths stretching west, east, and into the Americas. Wrangel Island's last mammoths. Ice winds sweep across Wrangel Island and drift ice presses against its shores, but beneath that chill lies a last echo of a lost world, the final mammoths. For millennia they walked where no other mammoths remained, holding out long after mainland herds vanished. Their persistence and ultimate fate remain one of Siberia's most haunting mysteries. Radiocarbon and Bayesian age models show that mammoths died out on the Siberian mainland well before disappearing on Wrangel Island. As sea levels rose after the last glacial maximum, mammoth populations became isolated on the island, cut off from migration corridors. That isolation lasted roughly 6,000 years, until around 4,000 years ago, when the last mammoths died out. Whole populations that had once ranged across the mammoth steppe were reduced to this island's remnant herd. Genomic analyses of Wrangel mammoths compared with older mainland specimens reveal intriguing contrasts. The island population shows evidence of a strong bottleneck, a drastic reduction in effective population size as they became stranded. Their genetic diversity shrank, and harmful mutations began accruing. Many genomic variants in the Wrangel line are predicted to be deleterious: loss of function in olfactory receptors, urinary protein genes, and potentially even pigmentation or developmental pathways. This accumulation of harmful alleles is sometimes called a genomic meltdown. Yet recent work complicates that narrative. A 2024 genome-scale study of 24 Wrangel specimens finds that the population remained more stable than previously thought. It shows little evidence of runaway inbreeding or catastrophic loss of genetic health. The mammoths may have tolerated low diversity without collapsing gradually. That suggests that the final extinction may not stem from genetics alone. At the same time, isotopic studies of bone and tusk collagen suggest that, even in the island's late period, mammoths maintained consistent diet signatures. Their feeding ecology did not shift dramatically even as climate warmed. The isotope values of carbon and nitrogen remained stable right up until their disappearance, implying that their habitat, forage base, and nutritional niche held until the end. So the puzzle deepens. These mammoths survived in isolation for thousands of years, with limited habitat, limited gene pools, and limited refuges, yet remained viable until a final collapse. What tipped them over? One candidate is climate change and environmental stress. As the Holocene progressed, regional warming, precipitation shifts, thawing permafrost, and vegetation changes likely altered plant communities. The mammoth steppe, dry, open grass and forb systems, gradually gave way to wetter tundra and shrublands, less suitable for large grazers. Seasonal extremes might have increased. Deeper snow, spring melt runoff, winter icing, or periodic extreme weather events could stress animals or reduce forage availability. On a small island, a bad winter or multi-year drought could decimate populations already living near environmental margins. Another suspect is chance catastrophe, disease, sudden climate anomaly, or a major fire or drought. On an isolated island with a small herd, a single event, epidemic, freeze, or habitat shock could wipe out the last survivors. Genetic models that show stable diversity until the end hint that extinction may have been sudden, not a drawn-out decline. human impact is harder to pin down. Evidence for human presence on Wrangel comes late. People arrived only in the island's final prehistory, some centuries after mammoth extinction in many reconstructions. That low overlap weakens the case for hunting as the direct cause, yet humans may have indirectly influenced habitat or introduced disease vectors. The coincidence in time suggests caution in ruling out any role. Modelers construct extinction simulations, combining reduced population size, environmental stresses, genetic load and chance events. Many runs suggest that mammoths on Wrangel lived near a viability threshold. Slight variation in birth rates, mortality or climatic stress could push them past tipping points. In a stable environment they managed, in a bad stretch they collapsed. One factor often modelled is the LA effect. In tiny populations, social structure, mating encounters, or cooperative behaviours break down. If too few individuals remain, reproduction and herd cohesion become harder. That may amplify vulnerability beyond just genetics or climate. Another interaction is genetic load x-environment. Deleterious alleles may remain tolerable until environment becomes harsher. A gene variant that is mildly harmful might be buffered in good conditions, but in drought or cold stress, that extra physiological cost could push individuals into decline. Thus, genetic stress and environmental pressure may have a lethal synergy. Even the long persistence suggests resilience. Mammoths survived earlier population crashes, climate shifts and isolation. Their biology allowed endurance. Their diets, reproductive rates and foraging flexibility gave them flexibility. That they lasted so long speaks to adaptation, not fragility. Still, the abruptness of their final disappearance raises the possibility that extinction was dominated by a rare shock, a collapse event rather than slow attrition. In a population of a few hundred or fewer, stochastic events loom large. A severe multi-year winter, permafrost thaw-driven floods, or even a pathogen introduced by humans could have triggered collapse. As researchers dig deeper, they search for supporting evidence. Paleo-environmental cores around Wrangel to detect fire scars, pollen shifts, or drought layers. Pathogen signatures in ancient DNA from mammoth remains, fine-grain age distributions to detect last survivors, and further genome sequences to detect late-stage stress signals. Each new data point is a clue. To reconstruct deep time is to walk on fractures of uncertainty. The last mammoths are detectable only by bones and genes. Their survival in isolation, genetic stress, stable ecology, and sudden end narrator system harnessed by climate, chance and biology. In the calm tundra of Wrangel Island, the bones lie quiet. But in their molecules and isotopes lies a final detective puzzle of life at the edge of extinction. How did Baikal's freshwater seal get there? Winter light glints across the frozen surface of Lake Baikal, the deepest lake on Earth and one of the oldest. Beneath that ice, among the clear depths that stretch for more than a kilometre, swims a creature that should not be there. A seal far from any ocean. The Baikal seal, or Nerpa, is the only seal in the world that lives entirely in freshwater. How it reached this remote inland lake remains one of Siberia's enduring biological puzzles. Everywhere else on Earth, true seals live in the sea, in Arctic ice, coastal fjords, or subpolar waters. Yet here, more than 2,000 kilometres from the nearest ocean, they dive for fish and sleep on ice floes. Biologists have long asked how a marine mammal managed to become trapped in a freshwater world and survive there for hundreds of thousands of years. The mystery begins with genetics. Studies of the Baikal seal's DNA show it is most closely related to the ringed seal, a marine species that lives throughout the Arctic Ocean. Their genomes diverged roughly 400,000 years ago, meaning the ancestor of Baikal seals must have entered the lake sometime in the Middle Pleistocene. That was a time when glaciers advanced and retreated, rivers shifted, and northern ecosystems were repeatedly reshaped by climate cycles. One leading theory says the ancestor of the Baikal seal swam inland from the Arctic Ocean through the Yenisei River, moving upstream through an ancient network of rivers that once connected to the Angara, the only outlet of Lake Baikal today. During periods of glacial melting, when sea levels and river flows changed, such routes might have been navigable. Seals could have followed fish migrations or ice corridors, gradually moving inland until some reached the Baikal basin and stayed there when connections closed. An alternate theory suggests that a chain of vast Pleistocene lakes once stretched across western Siberia, forming temporary links between the Arctic basin and Baikal. As climate oscillations reshaped the land, those lakes filled and drained. In that shifting network of water, seals may have crossed from one basin to another, eventually reaching Baikal before being stranded as water levels fell and basins dried or disconnected. Both ideas fit the broad picture, but neither can be proven. No fossil record of intermediate populations has yet been found along those routes. The lack of direct evidence means researchers must work with indirect clues, DNA divergence times, geological reconstructions, and comparisons with other inland seals, such as those living today in the Caspian and Ladoga lakes. The Baikal seal's genome tells a story of long isolation. Genetic diversity within the population is lower than in Arctic relatives, showing that it began with a small founder group and has remained separated ever since. Yet the seals appear healthy, suggesting that natural selection and a large enough population size prevented the harmful effects of inbreeding. Their physiology shows signs of adaptation to a purely freshwater life. They drink from the lake, regulate salt differently from marine seals, and feed on Baikal's endemic fish and amphipods. Isotopic analysis of bones and teeth reveals that their diet is built around pelagic prey, mostly the golomyanka fish, a small translucent species that lives in the lake's deep cold water. Baikal seals can dive to depths exceeding 400 meters, far beyond most freshwater species. Their blubber is thick, their blood oxygen stores large, and their metabolism tuned for long dives in dark, near-freezing water. Every part of their biology speaks of adaptation to this unique ecosystem. That adaptation likely unfolded over tens of thousands of generations. Climate, geography, and evolution formed a system that turned a marine wanderer into an inland specialist. The lake itself provided stability. Baikal is one of the most ancient and constant freshwater bodies on Earth, with liquid water in its depths even during the coldest glacial periods. Its ecosystem persisted through ice ages, offering refuge while shallower basins froze or dried out. But how many seals originally made the journey? And did the invasion happen once or in several waves? Some models suggest a single colonization event around 400,000 years ago. Others propose multiple introductions over successive interglacial periods. Each scenario depends on how often northern rivers and lakes connected to Baikal's basin, which in turn depended on glacial meltwater, permafrost, and shifting topography. Sediment cores taken from Baikal's basin record those climate swings. Layers of diatom shells, pollen and silt show cycles of warming and cooling, drought and flood. During interglacial periods, when the region was warmer and wetter, large river networks could have formed corridors. During glaciations, ice dams or expanding permafrost might have closed them. The ancestors of Baikal seals may have moved during one of those short open windows when water routes linked Arctic seas to interior basins. Another dimension of the mystery comes from comparing Baikal seals with the Caspian and Saimaa seals. All three descend from Arctic lineages that became isolated in inland waters during high sea level or meltwater phases, but their timelines differ. The Caspian seal became landlocked when the Paratethys Sea fragmented millions of years ago. The Saimaa and Ladoga seals were trapped only about 9,000 years ago after the last glacial retreat. Baikal's seals sit between those extremes, ancient enough to be distinct, recent enough to retain Arctic ancestry. Researchers reconstruct this puzzle as an interplay between migration, adaptation, and isolation. A small group of Arctic seals found their way into the Baikal basin, possibly through the Yenisei-Angara corridor, at a time when rivers ran high and ice retreated. Over millennia, cut off from the sea, they adapted to fresh water, evolved new traits, and became genetically distinct. Their population grew to occupy the entire lake, now numbering around 100,000 individuals. Modern genomic studies continue to refine the timeline. By comparing mutation rates and demographic models, scientists estimate that the effective population size of Baikal seals declined slowly after isolation but stabilized long before modern times. There is no sign of a sudden bottleneck or collapse. That stability supports the idea of long-term adaptation rather than recent introduction. Baikal's ecosystem, however, is changing again. Warming temperatures, pollution, and shrinking ice cover threaten the delicate balance that sustained the seals for hundreds of thousands of years. Yet they remain resilient, diving beneath the ice as their ancestors once did, tracing the legacy of a journey that began in the Arctic Ocean. The question of how they arrived may never be answered with full certainty. What the evidence shows is a convergence of forces: glacial corridors, shifting rivers, ancient isolation, and the quiet power of evolution. In the silence beneath Baikal's ice, the seals still glide, their presence a living reminder of the paths once carved between sea and lake, between saltwater and fresh, between the open Arctic and the heart of Siberia. Lake Baikal's sponge die-off. Winter light glints across the frozen surface of Lake Baikal, the deepest lake on Earth and one of the oldest. Beneath that ice, among the clear depths that stretch for more than a kilometre, swims a creature that should not be there, a seal far from any ocean. The Baikal seal, or Nerpa, is the only seal in the world that lives entirely in fresh water. How it reached this remote inland lake remains one of Siberia's enduring biological puzzles. Everywhere else on Earth, true seals live in the sea, in Arctic ice, coastal fjords, or subpolar waters. Yet here, more than 2,000 kilometres from the nearest ocean, they dive for fish and sleep on ice floes. Biologists have long asked how a marine mammal managed to become trapped in a freshwater world and survive there for hundreds of thousands of years. The mystery begins with genetics. Studies of the Baikal seal's DNA show it is most closely related to the ringed seal, a marine species that lives throughout the Arctic Ocean. Their genomes diverged roughly 400,000 years ago, meaning the ancestor of Baikal seals must have entered the lake sometime in the Middle Pleistocene. That was a time when glaciers advanced and retreated, rivers shifted, and northern ecosystems were repeatedly reshaped by climate cycles. One leading theory says the ancestor of the Baikal seal swam inland from the Arctic Ocean through the Yenisei River, moving upstream through an ancient network of rivers that once connected to the Angara, the only outlet of Lake Baikal today. During periods of glacial melting, when sea levels and river flows changed, such routes might have been navigable. Seals could have followed fish migrations or ice corridors, gradually moving inland until some reached the Baikal basin and stayed there when connections closed. An alternate theory suggests that a chain of vast Pleistocene lakes once stretched across western Siberia, forming temporary links between the Arctic basin and Baikal. As climate oscillations reshaped the land, those lakes filled and drained. In that shifting network of water, seals may have crossed from one basin to another, eventually reaching Baikal before being stranded as water levels fell and basins dried or disconnected. Both ideas fit the broad picture, but neither can be proven. No fossil record of intermediate populations has yet been found along those routes. The lack of direct evidence means researchers must work with indirect clues: DNA divergence times, geological reconstructions, and comparisons with other inland seals, such as those living today in the Caspian and Ladoga lakes. The Baikal seal's genome tells a story of long isolation. Genetic diversity within the population is lower than in Arctic relatives, showing that it began with a small founder group and has remained separated ever since. Yet the seals appear healthy, suggesting that natural selection and a large enough population size prevented the harmful effects of inbreeding. Their physiology shows signs of adaptation to a purely freshwater life. They drink from the lake, regulate salt differently from marine seals, and feed on Baikal's endemic fish and amphipods. Isotopic analysis of bones and teeth reveals that their diet is built around pelagic prey, mostly the Golomy anchorfish, a small translucent species that lives in the lake's deep cold water. Baikal seals can dive to depths exceeding 400 meters, far beyond most freshwater species. Their blubber is thick, their blood oxygen stores large, and their metabolism tuned for long dives in dark, near-freezing water. Every part of their biology speaks of adaptation to this unique ecosystem. That adaptation likely unfolded over tens of thousands of generations. Climate, geography, and evolution formed a system that turned a marine wanderer into an inland specialist. The lake itself provided stability. Baikal is one of the most ancient and constant freshwater bodies on Earth. With liquid water in its depths even during the coldest glacial periods, its ecosystem persisted through ice ages, offering refuge while shallower basins froze or dried out. But how many seals originally made the journey? And did the invasion happen once or in several waves? Some models suggest a single colonization event around 400,000 years ago. Others propose multiple introductions over successive interglacial periods. Each scenario depends on how often northern rivers and lakes connected to Baikal's basin, which in turn depended on glacial meltwater, permafrost, and shifting topography. Sediment cores taken from Baikal's basin record those climate swings. Layers of diatom shells, pollen, and silt show cycles of warming and cooling, drought and flood. During interglacial periods, when the region was warmer and wetter, large river networks could have formed corridors. During glaciations, ice dams or expanding permafrost might have closed them. The ancestors of Baikal seals may have moved during one of those short open windows when water routes linked Arctic seas to interior basins. Another dimension of the mystery comes from comparing Baikal seals with the Caspian and Saimaa seals. All three descend from Arctic lineages that became isolated in inland waters during high sea level or meltwater phases, but their timelines differ. The Caspian seal became landlocked when the Paratethys Sea fragmented millions of years ago. The Saimaa and Ladoga seals were trapped only about 9,000 years ago after the last glacial retreat. Baikal seals sit between those extremes, ancient enough to be distinct, recent enough to retain Arctic ancestry. Researchers reconstruct this puzzle as an interplay between migration, adaptation, and isolation. A small group of Arctic seals found their way into the Baikal basin, possibly through the Yenisei-Angara corridor, at a time when rivers ran high and ice retreated. Over millennia, cut off from the sea, they adapted to fresh water, evolved new traits, and became genetically distinct. Their population grew to occupy the entire lake, now numbering around 100,000 individuals. Modern genomic studies continue to refine the timeline. By comparing mutation rates and demographic models, scientists estimate that the effective population size of Baikal seals declined slowly after isolation but stabilized long before modern times. There is no sign of a sudden bottleneck or collapse. That stability supports the idea of long-term adaptation rather than recent introduction. Baikal's ecosystem, however, is changing again. Warming temperatures, pollution, and shrinking ice cover threaten the delicate balance that sustained the seals for hundreds of thousands of years, yet they remain resilient, diving beneath the ice as their ancestors once did, tracing the legacy of a journey that began in the Arctic Ocean. The question of how they arrived may never be answered with full certainty. What the evidence shows is a convergence of forces: glacial corridors, shifting rivers, ancient isolation, and the quiet power of evolution. In the silence beneath Baikal's ice, the seals still glide, their presence a living reminder of the paths once carved between sea and lake, between saltwater and fresh, between the open Arctic and the heart of Siberia. Zelony Yar mummies, Yamal. A biting wind sweeps over the floodplain of the Polui River in the Yamal tundra, where a grove of simple wooden markers hides something extraordinary beneath the frozen soil. This is Zelony Yar, a medieval necropolis where bodies wrapped in birch bark, copper sheets, furs, and odd ritual accoutrements have emerged from permafrost, remarkably preserved, mysterious, and strangely decorated. There is no better stage for a forensic reconstruction of buried ritual, ancestry, and identity in the far north. In expeditions from 2013 to 2016, archaeologists uncovered 47 graves at Zelony Yar, among them many that preserved mummies rather than decayed skeletons. Some of these bodies were enclosed in multi-layered birch bark cocoons, wrapped as if in a shroud and buried in shallow pits about 35 to 45 centimeters deep. In one exceptional case, burial hash 53, the body lay within a rectangular cocoon of birch bark overlapping layers, oriented along a north-south axis with slightly westward tilt. When the cocoon was peeled away, inside was the body, draped in fur veils and cloaked in copper plates covering face, chest, thighs, a metal mask of sorts over the flesh. Radiological scans show that internal organs remain, collapsed and shifted but still present inside body cavities. In CT images, the organs have slumped toward the back due to gravity and dehydration over centuries, yet lung, liver, and even brain remnants are visible. Histological study under microscopes revealed that much of the tissue has dehydrated. Cell walls are gone, nuclei dissolved, but collagen fibers remain, giving structure to what would otherwise be lost. In other mummified examples across the world, similar patterns emerge. Connective tissues preserve even when soft cells vanish. In the grave with the copper mask, beneath the copper sheeting lay layers of fur and bast fibre like robes. The copper did more than decorate. It acted as a barrier, shielding the body from moisture and microbial infiltration. In some cases, fragments of copper kettles or sheets surround infants, whose faces were masked by small copper plates. The metal, the bark cocoon, and the cold permafrost together created microclimates of preservation. Whether the copper was meant for mummification or ritual is unclear. Some bodies in the same cemetery lacked copper, so it was discretionary or status-based, not universal. From DNA extracted from bone and soft tissue, the mitochondrial haplogroups fall into 5 lineages: U5A, H3AO, U4B1B1D, and D4J8. These are a mix of Western and Eastern Siberian maternal lines. That means the people buried here had ancestry both from West Eurasia and East Asia, a blending of genetic backgrounds suited to frontier zones. That mixture suggests that Zelony Yar was a crossroads of population currents in medieval Siberia. One intriguing pattern: many of the burials share a consistent orientation. Feet pointing toward the Poli River, head to the south. This alignment may hold ritual significance. Water, rivers, death, and the cardinal directions often intersect in indigenous beliefs. The coverage of copper on the face and body may be symbolic, a mask for the journey to the afterlife or an expression of status, or perhaps a technology of preservation that grew from symbolic traditions. Artifact contexts deepen the puzzle. In several graves, archaeologists found bronze or silver ornaments, iron hatchets, bronze bowls, pendants, and metalwork that stylistically connects to regions far to the south. Some metal objects show design motifs that echo Persian or Central Asian styles, raising possibilities of trade, long-distance contact, or shared cultural threads. If true, the men and women at Zelony Yar were not isolated tundra dwellers but participants in a larger network of medieval Eurasian exchange. The forensic record also examines wear on bones and body morphology. Some individuals show osteological traits of robust build, habitual heavy loads, or joint wear consistent with a lifestyle of river travel, hunting, and material transport in cold zones. Though full life histories are elusive, the bodies show signs of adaptation: dense bone structure, evidence of nutrient stress or disease in a few, and healed injuries in others. The copper-clad man, for example, had a red hair pigment trace in his skull, perhaps from diet or genetic trait, but his physical stature and bone structure suggests someone of high status or importance in his community. The reconstructed sequence of burial practices reveals multiple steps. First, the person might be dressed in furs or garments, then wrapped in bast cloth or fibre, then wrapped in birch bark layers, then, in select cases, overlaid with copper sheeting, and finally interred in shallow pits in sand or loamy soil. Over the centuries, permafrost froze these graves, halting decay. Some of the cocooned bodies show no signs of grave robbery or disturbance, preserving their assemblages intact. Still difficult to resolve is why copper was used. In medieval Siberia, copper was rare and precious. Its procurement, smelting, and shaping require technical skill. To fashion sheets or plates large enough to cover a body suggests a concerted effort and a belief in its importance. Was it metallation of ritual dress, a form of spiritual protection, a ritual of the elite? The fact that only some bodies have copper suggests stratification. Another question lies in dating and chronology. Dendrochronology and artifact typology place these burials in the 12th to 13th centuries. Some burials may date as early as the 11th, but most fit the High Medieval era. That is a period of shifting climates, rising trade routes, expansion of steppe polities, and intensifying east-west contacts. In that context, Zelony Yar may reflect a frontier community linking northern indigenous traditions to wider medieval Eurasian dynamics. Yet many identities remain opaque. We don't yet know the language spoken, the specific culture of the group, or whether they were Nenets, Khanty, or a distinct group whose memory vanished. The mix of Western and Eastern Siberian ancestry suggests a hybrid or mixed-lived people. The prominence of males and infants among copper-masked mummified bodies and the relative rarity of adult female burials pose questions about gender roles, burial selection, and ritual hierarchy. In forensic reconstruction, The bodies at Zelony Yar are not inert remains, but stories frozen in time. Someone carefully dressed, masked, wrapped in bark, then laid to rest with care. We can map the steps of preparation, but not always the meaning. We can trace ancestry, but not the language. The bones show wear, the DNA shows mixture, the metal shows status, the alignment shows belief. Zelony Yar stands as a whisper from medieval Arctic Siberia, a place of cold isolation but not solitude. The copper masks glint in radiographic sequences. The collagen fibres retain texture under microscopy. Mitochondrial sequences link them to both east and west. In the birch bark cocoons they rest, neither fully buried in obscurity nor fully revealed to us. We reconstruct them piece by piece, lab by lab, hoping that the next fragment, the next isotope or gene sequence moves us deeper into their world. The Siberian Traps and the Great Dying. A cold hillside of Siberia holds a secret, older than all but a few things on Earth, a scar of fire and rock that may have nearly ended life itself. Beneath those basalt sheets lie the Siberian Traps, one of the largest volcanic provinces ever, whose great flood basalts erupted during the end of the Permian, about 252 million years ago. The timing matches the worst extinction in Earth's history, the Great Dying, when nearly 96% of marine species and 70% of land species vanished. But connecting lava flows to the deaths of so many creatures demands detective work, and every clue leads to more questions. The first clue is timing and volume. Geologists have mapped the Siberian Traps across millions of square kilometres, with erupted and intruded magma volumes in the millions of cubic kilometres. The lava flows, dikes and sills lasted over hundreds of thousands to perhaps 2 million years, overlapping the Permian-Triassic boundary. The closeness of eruption pulses to extinction horizons suggests a causal link. The volcanic activity was not a side effect but probably a trigger. But the traps alone are not a biological disaster. Many large volcanic provinces exist without causing global collapse. What made Siberian Traps different? To answer that, scientists look at the setting. Beneath the flood basalts lies the Tunguska basin, filled with thick sedimentary sequences of coal, organic shales, carbonates, evaporates, and gas-rich layers. When hot magma or sills intruded into those sediments, heat would bake coal seams, evaporite layers, carbonates, and gas fields, releasing massive volumes of carbon dioxide, methane, sulfur, halogens, and heavy metals. That internal combustion multiplies the effect of lava flows. Field evidence confirms this. In the southern regions of the traps, volcaniclastic rocks show charcoal, burned organic matter, and altered coal strata, tied in timing to early eruptions. That suggests magma literally caught sediment by fire, igniting coal and organics. The intrusion of sills into these layers may have triggered pulses of greenhouse gas release. One smoking gun in geochemistry is nickel anomalies. Sediments around the Permian-Triassic boundary show spikes of nickel, zinc, and lead, beyond expected background levels. That pattern points to the Siberian trap magmas, enriched in nickel, spraying aerosolized metal particles into the atmosphere. These metals may have fertilized marine microbes such as methanogens, which in turn would produce methane, a powerful greenhouse gas. So you get a positive feedback loop. Volcanoes release metals, stimulate microbes, pump methane, warm the planet further. Another important clue is sulfur. The gases from eruptions, especially sulfur dioxide, can create acid rain, block sunlight, and lower global temperatures temporarily. But when sulfur aerosols settle out, warming dominates. Sulfur isotope studies link sulfate aerosols from Siberian outgassing to terrestrial extinction signals. That is, the gases travelled far and affected climate and acidity globally. What about oceans? There, the effects may be strongest. The injection of huge CO2 into the atmosphere warms the planet and reduces oxygen solubility in water. That fosters ocean stagnation, anoxia, and even euxenia, oceans rich in hydrogen sulfide. Many marine fossils across layers show a shift to low oxygen indicators, black shales, redox-sensitive metals, and biomarkers of sulfur bacteria. This pattern is consistent with oceans suffocating, but which came first? Warming, acidity, oxygen collapse? It's a systems puzzle. Likely simultaneous stressors converged. CO2 increase, methane release, acidification, metal poisoning, and oxygen collapse, all pushing ecosystems beyond resilience thresholds. On land, warming plus acid rain destroyed plant life, causing soil erosion, habitat loss, and disruption of food chains. Fire spikes are recorded in charcoal records, showing wildfires likely increased. Another component is mercury. Elevated mercury concentrations in boundary layers suggest that volcanic eruptions vaporized mercury present in sediments, dispersing it worldwide. Mercury is toxic to life, especially to aquatic and terrestrial organisms at low concentrations. That toxic metal stress may have stressed organisms already weakened by other pressures. Yet the biggest twist in recent work is the recognition that not just surface lava matters. The intrusive pulse of magma below the surface, sills, may have been the worst killer. Studies argue that as magma spread horizontally through sediment layers, it heated them deeply, triggering the release of greenhouse gases in bursts over geological timescales. Surface lava may have come earlier and played a secondary role. The deeper sill emplacement overlapped exactly with the extinction interval. That model helps explain why extinction was abrupt. A slow drip of lava is devastating but gradual, but contact metamorphism of organic and carbonate layers by sills can produce sudden pulses of CO2, methane, and halogen gases. It's like pricking a tinderbox. And because these pulses release toxic gases, ocean perturbation, and warming collapse in sync, they make perfect killers. Yet the traps do not explain everything perfectly. Some kill mechanisms work better in marine context than terrestrial. Some models overpredict warming or ignore feedbacks. Also, fossil data from high latitudes, especially the boreal zones, shows the extinction may have begun earlier than the main pulse. That suggests the crisis was not instantaneous globally or varied by region. Another unresolved question: how long did ecosystems take to collapse, and was this a single pulse or multiple waves? Evidence of multiple extinction pulses suggests that the Siberian Traps induced a prolonged crisis, not a one-off kill. Ecosystems tried to recover, then relapsed. That aligns with the idea of volcanic activity over hundreds of thousands of years, not just a brief eruption. In modelling the system, researchers couple carbon cycle models, climate models, ocean circulation, biosphere feedbacks, and toxic gas release. Only some parameter combinations produce extinction-level outcomes. In many models, if CO2 increases too slow, life adapts. If it's too fast, collapse becomes near universal. The addition of methane pulses, metal fertilization, ocean feedbacks, and acidification make collapse more likely. But pinpointing which combination best fits fossil and geochemical data is still debated. Some models also explore ozone depletion. Volcanic emissions of halogens and sulfur may deplete stratospheric ozone, letting harmful UVB radiation reach surface life. That would stress plants and surface organisms. Modelling shows UV effects may play a supplementary role, but many think they cannot alone drive the mass extinction, because sulfate aerosols reduce UV transmission too, but the complexity is part of the puzzle. Thus, in deep time, the Siberian Traps stand as a crime scene. The suspects include CO2 overload, methane burst, sulfur and halogen poisoning, metals, acid rain, ocean anoxia, and ozone damage. Each mechanism has evidence and gaps, but the synthesis is clear. The Siberian Traps provided the heat, the fuel, and the spark. The sediments underneath provided the combustible material. The ocean and atmosphere did the rest. In burned rock, in metal traces, in carbon isotopes, in fossil collapse, the detective sees the fingerprints. But the case remains open in detail, even while the verdict that this volcanic upheaval nearly wiped out life looms over Earth's history. Popigai impact crater diamonds. In the remote tundra of northern Siberia, where rivers thread through grey stone and endless taiga, lies a crater so vast it can only be seen properly from the air. It spans about 100 kilometers across, a scar from an event that happened 35 million years ago. This is the Popigai crater, the fourth largest confirmed impact structure on Earth, formed when an asteroid or comet slammed into what was then a shallow landscape of graphite-rich rock. The collision vaporized bedrock, melted crust, and in an instant created one of nature's strangest materials, a field of diamonds born not from time and pressure, but from violence. The crater was first discovered in 1946 by Soviet geologists who noted the circular shape in aerial photographs. It was later studied in detail during the 1970s, when teams from the USSR's Geological Institute reached the site by helicopter. What they found astonished them. Rocks shot through with microscopic diamonds, scattered through breccias and shocked metamorphic zones. Unlike the gem diamonds mined in kimberlite pipes, these diamonds were grey, industrial grade, and filled with deformation twins and inclusions. But they had one unusual property, an intergrown structure that sometimes resembled Lonsdaleite, a rare hexagonal form of carbon theorized to be harder than any known diamond. The conditions needed to form such crystals exist nowhere naturally except at the moment of impact. When the asteroid, perhaps 5 kilometers wide, struck the Earth at tens of kilometers per second, the shockwave compressed graphite-bearing rocks to millions of atmospheres of pressure and thousands of degrees. In fractions of a second, carbon atoms reorganized from layered graphite into diamond lattice. In some zones, the extreme shock shear created polycrystalline aggregates, clusters of tiny interlocking diamond grains, some only nanometers across. These zones remain embedded in the impact melt that cooled into a glassy matrix. Field mapping shows that the Popigai structure consists of an inner uplifted zone about 25 kilometers wide, surrounded by a ring of shattered crust, with radial faults extending outward. Shocked quartz, diaplectic glass and melt breccia testify to instantaneous metamorphism. The diamond-bearing layers occur mainly in graphite schists and gneisses that lay near the impact center. In those rocks, the graphite was converted wholesale into diamond under pressures estimated at 30-50 GPa. Experiments in the 1980s confirmed that such transformation thresholds match those created in high-velocity impacts, not deep crustal processes. When Soviet researchers analysed the recovered material under microscopes, they noticed something else. The diamonds weren't single crystals. Instead, they were mosaics of grains, tightly interlocked and full of planar defects. Those features made them more resistant to fracture than natural gem diamonds. In laboratory tests, some samples exceeded the hardness of standard industrial diamond grit. Later analyses described them as polycrystalline diamond aggregates with nanocrystalline substructures. Others proposed that some portions represented Lonsdaleite-like domains, formed where shear strain and shock temperature combined to favour hexagonal stacking of carbon atoms. The presence of Lonsdaleite-like material sparked debate. Pure Lonsdaleite has been identified in meteorites and small impact sites, but usually as minute inclusions. At Popigai, the apparent abundance seemed unprecedented. Some researchers argued that the hexagonal signature seen in X-ray diffraction could result from stacking faults in cubic diamond, not true Lonsdaleite. Others maintained that the shock path and cooling rate indeed stabilized hexagonal diamond in transient zones before reverting to cubic. Even today, electron microscopy reveals a continuum between hexagonal, cubic and heavily faulted polytypes, showing that Popigai's diamonds represent a unique transitional fabric between forms of carbon. Overlying melt sheets show vesicular glass, spherules and flow textures that indicate post-impact drainage of molten material. Radiometric dating of impact glass gives an age of about 35.7 million years, coinciding with the Eocene-Oligocene boundary and aligning with other impacts like Chesapeake Bay and Tom's Canyon in North America. This global cluster of impacts may represent a comet shower or asteroid breakup event that peppered Earth at that time. During the Cold War, Popigai was classified for decades. Soviet authorities recognized its potential as a diamond source, but also its geological importance. Reports of its industrial diamond wealth led to speculations of secret exploitation. In reality, its remote location and difficulty of extraction limited operations. Only small amounts of Popigai diamond were recovered for research. Still, its potential industrial value is vast. Billions of carats are estimated to exist within the crater rocks. Yet their small grain size and diffuse distribution make mining uneconomical with current methods. Microscopic examination of Popigai samples reveals shock lamellae, graphite relics, and melted glassy pockets where carbon partially reverted during cooling. Each sample is a record of a few seconds of chaos frozen in stone. In thin section, carbon phases intertwine: graphite, diamond, amorphous carbon, and traces of carbide. Those textures help reconstruct the sequence: first compression and transformation, then rebound and rapid quenching. The crater became both a geological archive and a laboratory for natural high-pressure experiments. Comparisons with artificial shock experiments support this reconstruction. Laboratory simulations firing projectiles into graphite targets at hypervelocity reproduce microstructures almost identical to Popigai's. That confirms that the site is a natural analogue for impact-generated diamond synthesis, a process humans now replicate in high-pressure presses. But the natural material remains distinctive, its polycrystalline fabrics forming under more chaotic, non-equilibrium conditions than any industrial press can mimic. Some studies focus on trace inclusions inside the Popigai diamonds, tiny grains of iron-nickel metal, silicate glass, and sulfide droplets that formed simultaneously. These inclusions reveal the fluid and melt composition during impact, offering clues about oxidation state and temperature. Others examine isotopic ratios of carbon, finding that the source graphite was sedimentary in origin, not mantle-derived, further proving the shallow crustal target hypothesis. That connection links Popigai's diamonds to the surface carbon cycle, showing how even sedimentary carbon can be metamorphosed by cosmic trauma. The physical properties of these diamonds remain under active study. Some are tougher but less transparent than natural gems. Their fracture patterns, hardness variations, and thermal conductivity suggest potential uses in abrasives, drill bits, or electronics. The nanocrystalline texture dissipates cracks more efficiently, making them superior for certain mechanical applications. But the extreme small size of individual grains, often under a micron, limits cutting use. Scientists view them as a model for designing synthetic nanodiamonds rather than as a direct resource. In geological context, Popigai also helps calibrate planetary processes. By studying its shock metamorphism, researchers refine our understanding of crater formation on Earth, Mars, and the Moon. The concentric faults, uplift structures, and melt volumes correspond closely to those modelled for large planetary basins. Popigai stands as an analogue for how impacts reshape crust, redistribute materials, and create exotic minerals. Even after decades of research, disagreement persists about precise formation pathways. Did all the diamonds form instantly at maximum shock, or did some grow during decompression as temperatures remained high but pressures fell? Some evidence suggests a two-stage process. First, rapid graphite to diamond conversion under shock, then annealing and reorganization during cooling that produced the polycrystalline textures. Others argue for vapor deposition within the impact plume. Each model explains part of the data, but not all. When modern teams revisit the crater, they find weathered melt sheets and impact breccias still glittering with microscopic diamond particles. The tundra remains silent except for the wind, but within its rocks lies proof that the line between destruction and creation can blur in a single moment. In a few seconds of unimaginable force, common graphite was turned into one of the hardest substances known. A reminder that deep time hides not only fossils and extinction, but also crystallized violence left behind by a visitor from space. Batagay megaslump, Yakutia. In the frozen heart of Yakutia, deep within the permafrost belt of northeastern Siberia, a vast gash cuts across the land, a collapsing wound more than a kilometre long and over 90 metres deep. Locals call it the Batagay crater, though it isn't a crater at all. Scientists call it a megaslump, a feature born not from an impact or explosion, but from the slow, unstoppable thaw of the permafrost itself. It is one of the largest visible scars of a warming Arctic, a place where ice-rich ground, locked for tens of thousands of years, has begun to melt, buckle and slide away. Seen from above, Batagay looks like a tear in the earth. Its steep sides show layers stacked like pages in a geological diary. Each band represents an age of Siberia's past. Ice ages, interglacial periods, extinct ecosystems, all now exposed to air for the first time since the Pleistocene. When researchers descend into the slump with drills and coring equipment, they step into a cross-section of frozen history. The story of Batagay begins in the 1960s. Near the small settlement of Batagay, deforestation and road construction disturbed the ground cover that insulated the permafrost. Once the trees were gone, summer heat penetrated deeper, thawing the upper layers of frozen soil. In permafrost, ice is not just frozen water, it is the glue holding the ground together. When that ice melts, the land collapses. The first slump was small, just a few meters across, but over the following decades it grew dramatically. By the 1990s, it had reached hundreds of meters in width. By the 2010 satellite images showed it expanding at roughly 10 to 15 metres per year, consuming forest and tundra alike. At the core of the slump, the ice-rich sediments of Yadoma permafrost are exposed. Yadoma is a type of frozen ground formed during the late Pleistocene, composed of loess, silt, and massive wedges of ice. It is rich in organic matter, plant fragments, roots, and even animal remains, all preserved in frozen suspension for tens of millennia. When thawed, this material begins to decompose, releasing carbon dioxide and methane, greenhouse gases that feed back into the atmosphere, further amplifying warming. That makes Batagay not only a geological spectacle but a feedback engine in the climate system. Walking along its walls, researchers can read time itself. Radiocarbon dating of layers reveals alternating cycles of glacial and interglacial deposits stretching back more than 200,000 years. Fossilized pollen grains show shifts in vegetation, from steppe grasses and shrub tundra to boreal forests and back again. Each layer tells how the region's climate oscillated, recording ice ages and warmer phases with precision. In 2012, a local hunter found the frozen remains of a Pleistocene foal perfectly preserved in the slump. Its fur, hooves, and internal organs remained intact, sealed in permafrost for around 42,000 years. Later excavations uncovered bones and carcasses of mammoths, bison, and musk oxen. These discoveries make Batagay one of the most accessible windows into Ice Age ecology. It is both an open-air museum and a natural laboratory, where Thor reveals relics that have been hidden since humans first arrived in Siberia. But the megaslump is not stable. Each summer, thaw water runs down its sides, eroding more material. As the headwall collapses, new surfaces are exposed, accelerating the thaw further. Winter slows the process, but not enough to stop it. Measurements taken from drones and satellites show that the slump has deepened by nearly 20 metres in the past decade alone. Its rate of growth fluctuates depending on precipitation, temperature, and ground composition, making future predictions uncertain. Researchers from the Melnikov Permafrost Institute and other Arctic science centres have set up long-term monitoring stations around Batagay. They measure air and ground temperatures, ice content, and carbon fluxes. The goal is to understand how permafrost degradation feeds back into regional and global climate. The data show that once ice-rich permafrost begins to collapse, the process can become self-sustaining. Meltwater infiltrates deeper layers, destabilizing slopes and expanding the slump. Even if air temperatures were to stabilize, the ground may continue to fail for decades. The geometry of Batagay reveals the dynamics of permafrost failure. The uppermost layers, about 20 meters thick, consist of modern active layer soils, rich in roots and organic debris. Beneath that lie compacted loess and silt, laced with massive ice wedges that once expanded during Pleistocene cold seasons. As these ice wedges melt, they leave behind voids, causing overlying material to cave in. The slump's head wall retreats upslope, eating into higher terrain. The exposed walls often crack and shed slabs of frozen sediment, which slide to the base and melt into pools of turbid water. In some places, entire birch trees tilt and fall into the abyss, their roots still clinging to the upper tundra. The imagery evokes disaster, but to geoscientists, it's a living experiment. Each collapse exposes new layers, allowing sampling of permafrost that has never before been analysed. Stable isotope ratios in the ice show how precipitation sources changed over time, whether snow came from the Arctic Ocean, the Pacific, or continental sources. Organic carbon analyses reveal how much greenhouse gas potential lies locked in old soils. Microbiologists extract DNA from thawed sediments to study ancient ecosystems and microbial communities, mapping shifts in vegetation and fauna over millennia. In the lab, cores taken from Batagay's lower layers show alternating horizons of ice and silt, each horizon representing thousands of years of deposition. Some layers are rich in ancient peat, others in dust blown from glacial plains. These records link Batagay to global climate archives like Greenland's ice cores. Comparing isotopic signatures between them allows reconstruction of how Arctic Siberia responded to past global shifts, a clue to how it might respond now. Fieldwork in Batagay, however, is dangerous. The steep walls collapse without warning and the ground beneath researchers' feet can liquefy within minutes. Meltwater channels carve unstable gullies. Even standing near the headwall requires ropes and caution. Yet each field season, new teams return, drawn by the unprecedented opportunity to watch permafrost transition in real time. In satellite imagery, the Batagay megaslump looks like a funnel opening toward the west. Its shape hints at ancient valleys once buried by loess during the Ice Age. As thaw deepens, these valleys are re-exhumed, potentially re-establishing old drainage networks. That makes Batagay not only a geological hazard but a landscape transformer. Its meltwater feeds streams that carry sediment and organic carbon into the Jana river system, altering ecosystems downstream. Climate models struggle to account for such rapid, localized change. Traditional permafrost models assume gradual surface warming, but megaslumps like Batagay demonstrate nonlinear behavior. Once a slump begins, it can expand exponentially, creating a heat and moisture feedback that amplifies local thaw. The challenge is scaling these effects. One megaslump may seem small, but multiplied across Siberia's Yadoma fields, the released carbon could rival national emissions. In essence, Batagay is both a relic and a signal. A relic of the Ice Age revealing its buried archives, and a signal of the modern one erasing them. Every year, as permafrost softens and the megaslump widens, layers of ancient ground fall away, releasing air that hasn't touched the atmosphere in tens of millennia. Scientists record, measure and analyse, but the land continues to move faster than their models can predict. In the silence of the tundra, what once froze solid now flows, transforming the landscape and exposing the deep time of Siberia, one collapsing wall at a time. The 2002 Vitim fireball. On a cold Siberian night in late September 2002, the quiet of the taiga near Bodaibo was broken by something that sounded like the sky itself, tearing apart. Just after midnight on September 25th, a bright object streaked across the darkness over the Vitim River basin, turning night into day. People in small villages across the Irkutsk region saw the same thing. A glowing fireball followed by a flash so intense that shadows appeared on the snow, then seconds later, a deep rolling boom that shook windows and rattled roofs. That moment marked one of the most powerful meteor events on record since Tunguska in 1908. Yet, unlike Tunguska, the Vitim event occurred in modern times, in an era of satellites, seismic networks and video cameras, and still no one saw it coming. The first data came not from eyewitnesses, but from instruments. Seismic stations in Irkutsk, Yakutsk, and as far away as Mongolia recorded shock waves consistent with a mid-air explosion. The signals showed a pulse lasting several seconds, with energy release estimated between 0.2 and 0.5 kilotons of TNT, though some early estimates placed it closer to 1 kiloton. The epicenter was triangulated to a forested area about 60 kilometers southeast of the mining town of Bodaibo, near the upper Vitim River, a region so remote that it took researchers weeks to reach. The first expedition to the site took place in October 2002, led by a team from the Irkutsk State Technical University. They flew by helicopter into the dense forest and saw signs familiar to anyone who has studied cosmic impacts in Siberia: felled trees, scorched vegetation, and a circular pattern of damage. But the scale was smaller than Tunguska. Trees were toppled over an area of a few square kilometers, not thousands. Some trunks were snapped clean, others bent outward from a central zone, suggesting a shockwave expanding from above rather than an impact from the ground. Investigators found no crater. The absence of a crater meant that the object likely exploded in the atmosphere, disintegrating before reaching the surface. That type of event is known as an airburst, similar in nature to the Chelyabinsk meteor that would occur over the Ural Mountains 11 years later. At first, there was speculation of a small asteroid or a dense fragment of a comet. Some even wondered whether it could have been space debris re-entering the atmosphere, but eyewitness descriptions of colour and brightness, bluish-white light lasting several seconds brighter than the full moon, ruled out ordinary re-entry. The fireball's speed was consistent with a cosmic object entering the atmosphere at tens of kilometers per second. Subsequent expeditions over the next 2 years gathered more data. Researchers recovered fragments of silicate glass and magnetite spheres embedded in tree bark and soil. Laboratory analysis found high nickel and iron concentrations, suggesting extraterrestrial material. However, no solid meteorite fragments larger than a few millimeters were ever recovered. That left open the question of the object's composition. One model proposes that the Vitim bolide was a carbonaceous chondrite, a porous stony body that disintegrated easily in the atmosphere. Another hypothesis suggests it could have been a small icy comet fragment, perhaps related to the torrid orbits that produce periodic meteor showers. The way it exploded, high altitude, broad energy release, minimal crater, fits both models, but neither can be confirmed. The timeline of the event can be reconstructed from data across several networks. At 0:14 local time, the fireball entered the atmosphere, visible from hundreds of kilometers away. Villagers in Bodaibo, Mama and Taksimo described a long trail of light crossing the sky from south to north. A few seconds later, the flash intensified into a bluish flare that illuminated entire valleys. Windows shattered in nearby settlements as the shockwave arrived nearly 2 minutes after the flash. Animals panicked, and people ran outside thinking a plane had exploded. Military radar installations did not track the object, but US early warning satellites detected the infrared flare from the explosion. Later, declassified data placed the detonation at an altitude of around 30 kilometers. Atmospheric modeling of the acoustic waves that circled the globe confirmed an energy yield of a few hundred tons of TNT equivalent, enough to devastate a small area, but not enough to cause regional destruction. When the first snow melted the following spring, the Russian Academy of Sciences launched a joint expedition to revisit the site. They mapped treefall patterns, sampled soil, and used magnetometers to search for anomalies. The orientation of fallen trees and scorch marks suggested a trajectory from the south-southeast, entering at a shallow angle of about 20 degrees. The most damaged zone lay along a narrow corridor roughly 400 meters wide and several kilometers long, consistent with fragments from an object that broke apart in flight. Tree cores from the area showed distinct growth suppression rings after 2002, a biological record of the shock and heat stress. Carbonized leaves and shallow pits filled with vitrified sand indicated surface heating to several hundred degrees Celsius. Yet even here, researchers found inconsistencies. Some trees near the supposed epicenter remained upright, while others farther away were uprooted or burned. That uneven pattern raised doubts about whether the blast's main axis had been correctly located. To refine their model, scientists combined seismic, infrasound, and optical data. Infrasound waves, low-frequency sound inaudible to humans, travel long distances and are recorded by arrays worldwide. These signals confirmed a high-altitude detonation at about 56 degrees N, 113 degrees E. Energy release, altitude, and duration matched that of a small stony body between 5 and 7 meters in diameter, travelling at roughly 14-16 kilometers per second. That places the Vitim object within the same category as moderate near-Earth meteoroids that enter the atmosphere several times per year, though few reach this level of power. The forensic reconstruction, however, still faces uncertainties. No definitive chemical fingerprint exists, and the material evidence is fragmentary. One theory proposes that the Vitim body was an ordinary chondrite, partially dense enough to survive low in the atmosphere before exploding. Others argue the event's low altitude and energy ratio are better explained by a cometary fragment of low density but large size. Computer models of atmospheric entry simulate both scenarios. In the stony asteroid case, the object would have broken up at altitudes between 25 and 30 kilometers, generating multiple fragmentation waves. In the icy fragment case, disintegration would occur higher, between 35 and 40 kilometers, producing a broader but less intense shock. Observations of the sound delay and damage pattern favour the lower breakup, meaning a stony body may be more plausible. While the site never yielded a classic impact crater, several small depressions filled with water were noted by later expeditions. Geophysicists drilled one of these and found no meteoritic layer beneath, suggesting they are thermokarst pits formed by permafrost melting during the explosion's heat pulse. Comparisons to the 1908 Tunguska event are inevitable. Both occurred in Siberia, both caused treefall without a crater, and both remain only partially explained. Yet Vitim's energy was roughly 1,000th of Tunguska's. In Tunguska, about 2,000 square kilometers of forest were flattened. At Vitim, less than 1 square kilometer showed clear damage. Still, both illustrate how often small cosmic visitors strike the planet, and how easily they can escape detection until the moment of arrival. In the following years, atmospheric physicists continued analysing dust and ionospheric disturbances recorded after the blast. Satellites detected a temporary increase in upper atmosphere density, consistent with vaporized silicates. Meteor specialists matched the object's orbit backward, suggesting a possible link with the Taurid complex, known for its periodic streams of cometary debris. If correct, Vitim may have been part of that swarm, one of countless fragments travelling silently through near-Earth space. The forests around Bodaibo have since grown back. Scars of toppled trees have faded under new vegetation, but beneath the canopy traces remain: shock-melted minerals, magnetite dust, rings in tree trunks, and a patch of ground still slightly altered by heat. The Vitim fireball remains a case study in modern impact science, an event caught between evidence and mystery, between what instruments saw and what the ground preserved. In the darkness of that Siberian night, for a few seconds the sky opened, and a reminder of Earth's vulnerability burned across it before vanishing into the air. Ancient giant viruses revived from Siberian permafrost. Deep beneath the frozen ground of northeastern Siberia, where the soil has remained locked in ice since the Ice Age, scientists unearthed something that should not have been alive. And yet, somehow, it was. Hidden within the permafrost lay ancient viruses, tens of thousands of years old, still intact, still capable of infecting their hosts after thawing. In a laboratory in France under strict containment, these prehistoric microbes stirred again after 30 millennia of silence. It began in 2014, when a research team from the CNRS and Aix-Marseille University, led by microbiologist Jean-Michel Claverie, announced that they had revived a virus from a Siberian permafrost sample dated to about 30,000 years old. The sample came from the Kolyma lowland, a region known for frozen sediments rich in Pleistocene remains, mammoths, bison, woolly rhinoceroses, and now a virus large enough to be seen through a standard microscope. They named it Pithovirus sibericum. Under the microscope, it didn't look like any virus known at the time. Instead of being small and geometric like influenza or adenoviruses, it was giant, over 1.5 micrometers long, bigger than many bacteria. Its shape resembled an amphora, an oval body with an opening sealed by a cork-like structure. Despite being ancient, it was still infectious, though its hosts were amoebae, not animals or humans. When introduced into cultures of Acanthamoeba castellanii, the virus entered, replicated, and produced new viral particles, proving its viability after tens of thousands of years. The findings stunned virologists. Until then, it was believed that viral particles could not remain viable over geological timescales. Yet here was one that had survived since before the extinction of mammoths. The cold, oxygen-poor and stable conditions of the Siberian permafrost had protected its capsid, the protein shell, from degradation. That discovery opened an entire new field of study: paleovirology, the study of ancient viruses preserved in frozen or mineralized environments. Following that first success, the same team continued to sample permafrost layers. In 2015, they reported a second revival. Mollivirus sibericum, another 30,000-year-old giant virus, spherical in shape and distinct in genome structure. Later came Pandoravirus yodoma, megavirus mammoth, and Pacman virus lupus, all isolated from various permafrost samples collected in northeastern Russia. Each belonged to a different lineage of giant viruses, collectively known as nuclear cytoplasmic large DNA viruses, a group that blurs the line between viruses and cellular life due to their complex genomes and replication strategies. These viruses are enormous by viral standards, carrying hundreds or even thousands of genes, far more than typical viruses that depend almost entirely on the host's machinery. Their genomes encode enzymes once thought exclusive to cellular organisms, such as DNA repair and transcription proteins. That means they are capable of partial self-maintenance inside their host cells. The revival of these ancient viruses raises questions that stretch far beyond microbiology. In controlled lab conditions, they only infect amoebae, but the fact that any virus can survive so long challenges assumptions about the limits of biological preservation. It also poses an unsettling question. If viruses can remain infectious after tens of thousands of years, could others, potentially harmful to animals or humans, also survive in frozen ground? Permafrost covers about a quarter of the land in the northern hemisphere, and it stores not only ancient organic carbon but also the remains of countless organisms. As global temperatures rise, thawing exposes these long-sealed layers to air, water and microbial life. The release of ancient carbon is already known to accelerate climate change. Now, scientists are also watching for the biological consequences, the release of ancient microbes, some of which may have no modern equivalent. In 2016, a separate event in the Yamal Peninsula illustrated this risk. A heatwave thawed deep permafrost, releasing anthrax spores from a decades-old reindeer carcass. The outbreak killed one child and thousands of reindeer. Though anthrax is bacterial and not viral, the incident served as a vivid reminder that ancient pathogens can re-emerge when ice melts. In the case of pithevirus and its kin, strict safety protocols are followed. The samples are handled only under biosafety level 2 or higher conditions, and the experiments use amoebae as hosts precisely because they pose no danger to humans. Yet the broader implications remain part of ongoing research. If viruses infecting amoeba can persist, so might other, more complex pathogens, even if the probability is low. From a fieldwork perspective, the discovery process is meticulous. Teams extract permafrost cores using sterile drills, often from Yodoma deposits, frozen silt accumulated over tens of thousands of years. Each layer is logged, dated and sealed in sterile containers before being transported at sub-zero temperatures to laboratories. There, under controlled thawing, samples are screened for the presence of viral particles using electron microscopy and DNA sequencing. When a viral signature is detected, researchers attempt to cultivate it using known host species. Most remain inactive. Some degrade completely upon thawing, but occasionally a particle's genetic material remains intact enough to reassemble inside a host cell, beginning a new cycle of replication. Every successful revival provides a glimpse into ancient ecosystems where amoeba, algae, and microscopic predators interacted in ways that can still be reconstructed from DNA. Analyzing the genomes of these revived viruses has revealed clues to ancient environments. The sequences show adaptations to cold and nutrient-poor conditions, as well as similarities to viruses found in modern freshwater and soil ecosystems. That continuity implies that some viral lineages have persisted with little change for tens of millennia. They represent evolutionary holdovers, living fossils of the microscopic world. Each revived virus also helps calibrate models of long-term biological survival. Their intact DNA and proteins demonstrate that organic molecules can remain stable in frozen sediments for far longer than previously thought. That discovery extends beyond Earth. If viruses can endure 30,000 years in Siberian ice, similar mechanisms might preserve microbes on Mars or frozen moons like Europa and Enceladus. The permafrost becomes a testbed for astrobiology, offering direct evidence that life, or at least biological information, can persist in extreme cold and darkness. Still, researchers emphasize that these viruses are not zombies awakening on their own. They require lab conditions and a specific host cell to become active. Without those triggers, they remain inert, sealed in ice or soil. Yet as permafrost thaws across the Arctic, the potential for these dormant particles to mix with meltwater and soil, microbes, increases. Understanding their resilience and biology becomes essential not only for curiosity but for preparedness. The layers of permafrost are time capsules, each holding fragments of past life. Alongside plant pollen and animal bones lie microbial communities frozen since the last glaciation. In some samples, scientists have found bacterial DNA, fungal spores, and even microscopic algae, all preserved by cold and lack of oxygen. The viruses are part of that continuum, evidence that life, once sealed away, does not always stay gone. As scientists continue to probe the permafrost for ancient genomes, the questions grow larger than the samples themselves. What happens when the ice that has held them for millennia gives way? How many unknown species, microscopic and otherwise, remain locked beneath Siberia's frozen ground? And what stories, what warnings, still lie buried in that ancient thawing archive of time? Ice Maiden of the Altai, Pazyryk culture. High in the Altai mountains of southern Siberia, where the borders of Russia, Mongolia and Kazakhstan meet, a plateau of wind and silence guards one of the most remarkable archaeological discoveries ever made in the region. in the summer of 1993, a team of Russian archaeologists led by Natalia Polosmak uncovered a burial mound on the Yukok Plateau at an altitude of 2,500 meters. Inside the mound, beneath layers of stone and frozen soil, lay a wooden chamber sealed in permafrost. When the lid was lifted, they found a woman who had been buried more than 2,400 years ago, her body astonishingly well preserved, her skin still showing patterns of dark, curling tattoos. She would later be known to the world as the Ice Maiden, or sometimes the Princess of Yukok, a name that sparked fascination, debate, and even controversy across Russia. Her discovery offered an unparalleled window into the Pazyryk culture, an Iron Age nomadic society that thrived in the Altai during the 5th to 3rd centuries BCE. For the first time, archaeologists could see not only the artifacts of that world, but also the face and body of one of its people. The Ice Maiden was buried in a kurgan, a mound typical of Pazyryk elite burials. Her wooden coffin had been hollowed from a single larch trunk, tightly sealed and then frozen for millennia, preventing decay. Around her lay 6 horses, their harnesses decorated with felt and wood ornaments, and richly crafted objects made of gold, silk and wool. These offerings suggested she held a high position, possibly as a priestess, shaman or noblewoman. When conservators removed the linen wrappings, the body revealed extraordinary detail. Her arms, shoulders and fingers were covered with tattoos of mythological animals, deer with antlers curling into floral shapes, griffins and feline predators, all rendered with flowing lines that mirrored Pazyryk art motifs found on carpets and carvings. Radiocarbon dating placed her burial around the 5th century BCE, aligning her with other Pazyryk sites excavated in nearby valleys. Forensic analysis began immediately. CT scans and tissue sampling revealed that she was in her mid-20s at the time of death. Her hair, cut and styled into a long braid, was still intact, and her skin bore traces of herbs and pigments used in embalming. Researchers noted that her joints and muscles had been carefully packed with a mixture of moss and aromatic plants, likely to preserve shape and absorb moisture. Inside her coffin, alongside her clothing and jewellery, was a small container with traces of cannabis, consistent with known ritual uses in Pazyryk culture. One of the most intriguing findings came decades later, when advanced imaging and MRI scans were performed on her remains. The scans revealed a dark mass in her right breast and lesions in nearby bone, consistent with metastatic breast cancer. This diagnosis suggested that the woman had been gravely ill for years before her death. Her posture in the coffin, lying on her side, knees slightly bent, showed no signs of trauma, supporting the idea that she died of disease rather than violence. But the cause of death was only one layer of the story. For archaeologists, the arrangement of the burial chamber held deeper meaning. The horses, positioned carefully and decorated with wooden masks resembling mythical beasts, were likely meant to carry her into the afterlife. The presence of fine textiles, including fragments of Chinese silk, hinted at far-reaching trade networks linking the Altai to Persia, India, and the steppe routes that would later form the Silk Road. Her costume, a felt headdress rising high above the head, a silk blouse and a wool skirt, matched depictions of ritual figures known from Pazyryk iconography. The tattoos, preserved almost in their entirety, became a focal point of study. Using infrared photography and digital scanning, researchers mapped the ink patterns in detail. They found that her designs mirrored those seen on warriors from nearby Pazyryk burials, not as simple decoration, but as symbols of power, protection, or spiritual status. The tattoo of a stag with branching antlers on her shoulder may have represented transformation or guidance in death. In Pazyryk art, such creatures often appear as intermediaries between worlds. In cultural terms, the Ice Maiden revealed the sophistication of a society often labelled as nomadic. The Pazyryk people were skilled horse breeders, metal workers and artisans. Their frozen tombs, preserved by the Altai's permafrost, contain not only weapons and jewellery, but also the oldest known knotted carpets, musical instruments and medical tools. Each object in the maiden's tomb connected her to that broader cultural network, showing a people with artistic depth and a strong sense of ritual order. Yet her discovery did not come without controversy. Local Altai communities, particularly those identifying as descendants of the ancient Pazyryk, protested her removal from the burial site. Some elders believed disturbing her grave brought misfortune, and after her body was taken to Novosibirsk for study, reports of earthquakes and storms fueled legends that the princess had been angered. Years of negotiation eventually led to her partial return. In 2012, her remains were transferred to the National Museum of the Altai Republic in Gorno-Altaysk, where she now rests in a climate-controlled glass sarcophagus. The scientific work continued even after her repatriation. Pollen analysis from the coffin lining confirmed that the burial took place in early summer. The floral residues, from yarrow, thyme and other alpine plants, suggest a ritual connection to seasonal cycles. Textile analysis revealed the weaving techniques used for her garments were imported from Central Asia, supporting evidence of long-distance exchange. Stable isotope studies of her hair and teeth traced her diet and mobility, showing she consumed both local and imported food sources, possibly reflecting her elite status. The forensic reconstruction of her face, created in the early 2000s using cranial measurements and 3D modelling, gave her soft features, high cheekbones, light eyes, and a calm expression. This reconstruction, however, sparked debate. Some argued that artistic interpretation influenced the final image more than data, while others viewed it as a respectful humanization of the past. Either way, her face became an icon of Siberian archaeology, representing a civilization once considered lost. Through successive examinations, new signals kept emerging. Trace DNA analysis confirmed she belonged to an Indo-European population related to ancient Scythian and steppe groups, rather than East Asian lineages that later dominated the region. That genetic data, cross-checked with other Pazyryk remains, helped map ancient migrations across Eurasia. But noise persists in the data. Contamination, incomplete sequences, and gaps caused by permafrost thaw, leaving some details uncertain. Archaeologists working in the Altai still debate her exact social role. Was she a shaman who mediated between spirits and her people? A noblewoman linked to a ruling clan? Or a healer whose death required elaborate rites? The evidence supports all possibilities. Her burial symbolism, animals, herbs, and the arrangement of horses points to ritual importance. Yet the absence of weapons or tools of authority makes her role enigmatic. The Ice Maiden remains a rare fusion of art, medicine, and anthropology. Her tattoos preserve ancient aesthetics. Her illness reveals biological history, and her tomb preserves the structure of belief. Every new test adds another layer. Stable isotopes for climate, DNA for lineage, and tomography for pathology. But the signal always competes with the noise of time. What endures is her silent body, frozen not by accident but by the natural vault of the Altai permafrost, holding its secrets in the cold earth of the steppe. Across the frozen ground of Siberia, the past never fully sleeps. Every thaw, every dig, every new discovery opens another window into worlds long gone, and questions that remain unanswered. From ancient humans to cosmic impacts, from buried viruses to shifting Earth, the region continues to challenge what we think we know about our planet and its history.